Picture, if you will, the banks of the Tigris River over 1,000 years ago. A city of sandstone and marble, shimmering under a relentless sun, its bustling streets filled with the sounds of a dozen languages and the scent of spices carried on desert winds. This is Baghdad, but not just any city. For centuries, this was the beating heart of the world, a metropolis so advanced, so brimming with knowledge, that its light illuminated a world otherwise shrouded in shadow. And at the very center of this brilliance stood a legendary institution, a name that still echoes with the weight of discovery, the House of Wisdom. It was more than a library. It was a grand experiment, a magnetic force that drew the finest minds from across continents, all united by a single, audacious goal: to gather all the world's knowledge under one roof and push the boundaries of human understanding further than ever before. What did it feel like to walk those hallowed halls, to be surrounded by towering shelves stacked with scrolls from Greece, India, Persia, and beyond? We often think of history in broad strokes, empires rising and falling, wars won and lost, but the true magic, the real engine of human progress, is found in the quiet moments of discovery. It happened in the hushed conversations between a mathematician from Al-Khwarizmi and a translator from Syria, debating the intricacies of a Greek text. It happened under the flickering light of an oil lamp as an astronomer meticulously charted the motion of a distant star. This was a place where curiosity was the highest currency, and the scholars of Baghdad were its richest citizens. Their work wasn't just academic. It was a radical act of preservation and innovation that would, quite literally, shape the future of science, medicine, and philosophy for centuries to come. So what did these intellectual giants actually study? The answer is as vast as their ambition. Their fields of inquiry were not isolated silos but interconnected webs of knowledge, each one feeding into and enriching the other. They were mapping the heavens while also perfecting the algebra needed to navigate the earth. They were developing surgical techniques informed by a deep understanding of human anatomy, all while philosophers debated the very nature of existence and the soul. This journey we're about to take together is more than a history lesson. It's an invitation to step inside that world, to understand not just what they learned, but how they thought. We're going to explore the incredible diversity of scholarship that flourished in Baghdad, uncovering the stories of the men and women who dared to ask big questions and, in doing so, laid the groundwork for the modern world. This is the story of human curiosity at its most powerful, and it all starts here. But such an ambitious project required a foundation, a city built not just for commerce or defense, but for the mind itself. The story of this intellectual golden age begins not with a scholar, but with a caliph and a blueprint. In the year 762, the Abbasid Caliph Al-Mansur made a momentous decision. He chose a small village on the banks of the Tigris River as the site for his new capital, a city he would name Baghdad, the City of Peace. Its design was revolutionary, a perfect circle, often called the Round City, with the Caliph's palace and the Grand Mosque at its heart, symbolizing a new centralized order. This was more than just urban planning. It was a statement of intent. Al-Mansur envisioned Baghdad as the nerve center of a vast empire, and he understood that to rule effectively, he needed knowledge. He initiated the gathering of books, laying the initial groundwork for what would become a legendary repository. The project truly ignited under his successors, Caliph Harun al-Rashid, and most famously his son, Caliph al-Mamun. Harun al-Rashid, a figure immortalized in the tales of the Arabian Nights, transformed his father's collection into a formal institution, the Bayt al-Hikmah, or House of Wisdom. But al-Mamun, who reigned from 813 to 833, was the true architect of its glory. A philosopher caliph in his own right, al-Mamun was driven by an insatiable curiosity. He didn't just want a library, he wanted an engine of innovation. Under his passionate patronage, the House of Wisdom exploded into a multifaceted academy, a translation center, and an observatory all rolled into one. He actively dispatched emissaries to distant lands, to the Byzantine Empire and beyond, with chests full of gold to acquire the most precious treasures of the age, not jewels, but manuscripts. This became the institution's primary fuel: translation. Think of it as the most ambitious open-source project in history before the internet. Teams of scholars, often working in collaborative pairs, a native speaker of Syriac or Greek and a native Arabic speaker, would meticulously translate the entire corpus of known science and philosophy. They brought the works of Plato and Aristotle, the geometry of Euclid, the medical genius of Galen, and the astronomical theories of Ptolemy into the Arabic language. But they didn't stop there. They also absorbed the profound mathematical knowledge from India, including the revolutionary concept of zero and the sophisticated astronomical tables from Persia. This was not a simple act of copying. The scholars of the House of Wisdom were critical thinkers. They would annotate, critique, and build upon these texts, correcting errors and expanding theories, creating a new, synthesized body of knowledge that was greater than the sum of its parts. And this activity created an irresistible gravitational pull. The House of Wisdom became a beacon, attracting the greatest intellects from every corner of the empire and the known world. A mathematician from Al-Khwarizmi, a translator from Hunayn ibn Ishaq's school, an astronomer from Persia, and a philosopher from Baghdad itself could all be found working side by side. They were provided with salaries, spacious quarters, and, most importantly, unlimited access to the greatest collection of books the world had ever seen. This environment of supported, collaborative inquiry was its true genius. It was a place where a question posed in the translation room could spark an experiment in the observatory, and where a debate in the philosophy circle could lead to a breakthrough in medicine. The House of Wisdom was the physical embodiment of a radical idea: that knowledge has no borders, and that progress is achieved not by hoarding information, but by sharing it, debating it, and relentlessly pushing it forward. And so, with this unprecedented hub for learning established, the real work could begin. The first and perhaps most critical mission of the House of Wisdom was not originally to create new knowledge, but to save the old. This was the Great Translation Movement, a cultural and intellectual undertaking on a scale the world had rarely seen. Imagine entire libraries of ancient wisdom, the accumulated works of Greek philosophers, Persian engineers, Indian mathematicians, and Syriac physicians, sitting untranslated and slowly fading from memory. In the West, much of this knowledge had been lost or was languishing in inaccessible monasteries. The scholars of Baghdad saw themselves as guardians of this fragile inheritance. They understood that before they could advance, they had to preserve, and to do that, they needed a common language, a lingua franca for science. That language became Arabic. The process was far more sophisticated than simple word-for-word conversion. It was an act of deep scholarship and interpretation. At the forefront of this effort was a man named Hunayn ibn Ishaq, a Nestorian Christian who became the director of the House of Wisdom's translation activities. Hunayn was a master linguist, fluent in Arabic, Syriac, Greek, and Persian. His methodology was revolutionary. Instead of translating directly from Greek into Arabic, he would first translate a text into his native Syriac, ensuring he fully grasped its nuanced meaning. Then, he would collaborate with his son, Ishaq ibn Hunayn, or other colleagues to render the Syriac version into elegant, precise Arabic. This two-step process guaranteed accuracy and clarity, transforming dense philosophical and scientific texts into works that were not only correct but also readable and accessible to a new generation of scholars. Under Hunayn's leadership, teams of translators tackled the giants of classical thought. They brought the entire logic and natural philosophy of Aristotle into the Arabic-speaking world. They translated the medical encyclopedias of Galen, whose theories would dominate medicine for centuries. They rendered the geometry of Euclid and the complex astronomical models of Ptolemy's Almagest. But their ambition stretched beyond the Mediterranean. They eagerly sought out knowledge from the East, translating sophisticated Sanskrit texts on mathematics from India, which introduced the world-changing decimal system and the concept of zero. They absorbed Persian texts on statecraft, astronomy, and legendary stories, and Syriac Christian texts that themselves contained layers of translated Greek knowledge. This was not a one-way street of simply taking information. The translators were active, critical participants. They would write extensive commentaries, pointing out errors in the original texts, clarifying ambiguous passages, and updating information based on newer discoveries. A translation by Hunayn was more than a copy. It was a new, improved edition, enriched with the insights of a 9th-century scholar. This massive project did more than just fill the shelves of the House of Wisdom. It created a unified scientific vocabulary. Think of it as building a universal operating system for knowledge. A scholar in Cordoba could now read a text from Baghdad and know that the term al-jabr meant a specific mathematical operation, or that a certain anatomical term referred to a precise part of the body. This shared language allowed for unprecedented collaboration and debate across vast distances. The translation movement effectively built the foundation upon which all subsequent Islamic science would stand. By saving the works of the ancients from oblivion and refining them through a critical lens, the scholars of Baghdad ensured that this knowledge would not only survive, but would become the springboard for breathtaking new innovations. They turned the library into a living, breathing laboratory of ideas. With this unified library of world knowledge now speaking a common language, the stage was set for a revolution. And it was in the field of mathematics that the scholars of Baghdad made some of their most enduring and practical contributions, creating a toolkit that would become essential for scientists, engineers, and merchants for 1,000 years to come. Their work began with a simple but profound adoption that would change how humanity counts forever. Before the House of Wisdom, the world was using a patchwork of clumsy numeral systems. The Romans used letters, which made complex calculations incredibly difficult. In many places, merchants and astronomers relied on physical counting boards or abacuses. Then, scholars in Baghdad encountered a revolutionary system from India. It was deceptively simple, just 10 symbols, including a small circle that represented nothing. The concept of zero. This was a monumental leap. Think about trying to do long division with Roman numerals. It is nearly impossible. But with this new decimal system, with its place value meaning a 5 in the tens column is different from a 5 in the hundreds column, complex arithmetic became accessible. The scholars of Baghdad didn't just import these symbols, they refined them, popularized them, and integrated them into every facet of scientific and commercial life. From there, these numerals traveled west, eventually becoming the Arabic numerals we use every single day. It is difficult to overstate the importance of this. It was like giving the entire world a new, vastly more powerful brain for calculation. But mathematics was about more than just counting. It was about solving real-world problems, and one man's name became synonymous with that quest: Muhammad ibn Musa al-Khwarizmi. Working at the House of Wisdom in the early 9th century, al-Khwarizmi took the new numerical system and pushed mathematics into entirely new territory. His most famous work, the compendious book on calculation by completion and balancing, tackled a common issue: how to handle inheritances, land surveys, and complex contracts fairly. The Arabic word for completion, or restoring, is al-jabr. Yes, that is the origin of the word algebra. Al-Khwarizmi was essentially creating a system for solving equations, a set of rules for finding unknown quantities. He didn't use the symbolic X and Y we know today. He wrote everything out in words, but the concepts were their systematic methods for solving linear and quadratic equations. He was moving mathematics from a collection of specific arithmetic problems toward a generalized science of relationships. And from his name, al-Khwarizmi, we get the word algorithm, a step-by-step procedure for calculations, which is the absolute bedrock of modern computer science. His work provided a universal method, a logical framework that could be applied to problems in commerce, law, astronomy, and architecture. The drive to understand the heavens provided the next great challenge for these mathematical pioneers. Astronomy demanded precision, and precision required a new branch of mathematics, trigonometry. While the Greeks had laid some groundwork, it was scholars in the Islamic world, many centered in Baghdad, who transformed it into a powerful and independent discipline. Figures like Habash al-Hazib and later al-Battani produced incredibly accurate trigonometric tables. They systematically defined the sine, cosine, and tangent functions as ratios between the sides of a right-angled triangle. Why was this so crucial? For an astronomer trying to calculate the distance to the moon or the circumference of the Earth, these tables were an indispensable calculator. They allowed for the indirect measurement of distances that were impossible to reach. A scholar could measure an angle from a known location and then use these trigonometric relationships to compute a vast distance. This wasn't just theoretical. It had immediate practical applications for navigation, for determining the direction to Mecca for prayer, and for creating more accurate calendars. Their work in spherical trigonometry, essential for mapping the curved sky onto flat charts, was particularly advanced, solving problems that flat plane geometry simply could not handle. And their fascination with shape and space extended back to the foundations laid by the Greeks. The scholars of the House of Wisdom didn't just translate Euclid's Elements, the foundational text of geometry. They studied it, critiqued it, and attempted to prove its infamous fifth postulate, also known as the parallel postulate. This problem, which deals with the behavior of parallel lines, would puzzle mathematicians for centuries and eventually lead to the discovery of non-Euclidean geometry. While they didn't solve it, their intense scrutiny and commentary refined geometric thought. But their geometric skills were also intensely practical. They applied these principles to art and architecture, leading to the breathtakingly complex geometric patterns that adorn Islamic monuments. These are not just decorations, they are visual demonstrations of a deep understanding of symmetry, tessellation, and infinity. The work in mathematics was never an isolated pursuit. It was the essential language that connected every other field of study, from the music of the spheres to the precise cuts of a surgeon's blade. While algebra and geometry provided the tools for understanding the world on the ground, it was the sky above that presented the ultimate challenge, demanding a level of precision that pushed these scholars to their limits. The drive to map the heavens was not merely academic, it was woven into the very fabric of their society, determining the exact times for the 5 daily prayers, establishing the beginning of lunar months like Ramadan, and navigating the vast trade routes of the empire all relied on accurate astronomical knowledge. This practical need, combined with a profound philosophical desire to comprehend the cosmos, fueled an astronomical revolution centered in Baghdad. The scholars there inherited the complex geocentric model of the universe from Claudius Ptolemy, a system of intricate circles upon circles known as epicycles designed to explain the puzzling retrograde motion of planets. But rather than accepting it blindly, they engaged with it critically, testing its predictions against the cold, hard data of their own observations. This required more than just pen and paper. It required a new kind of scientific instrument on a monumental scale. The most tangible expression of this commitment was the construction of the first major observatories in the Islamic world, prototypes for the great scientific facilities we know today. While earlier astronomers might use a simple astrolabe, the scholars under Caliph Al-Mamun's patronage built permanent, dedicated structures. The most famous was the Shamsiyya Observatory in Baghdad itself. Imagine a grand building, its roof open to the stars, housing massive, precision-crafted instruments that were feats of engineering in their own right. They constructed giant meridian arcs, essentially enormous calibrated arcs fixed in the north-south plane, and massive quadrants, allowing them to measure the altitude of stars and planets with an accuracy previously unimaginable. This wasn't casual stargazing, it was a systematic, state-funded research program. The very existence of these observatories signified a shift towards institutionalized, evidence-based science, where hypotheses could be continuously tested and refined against a growing body of empirical data. One of their first great triumphs was a project that combined mathematical brilliance with raw physical effort, a new calculation of the Earth's circumference. The Greek Eratosthenes had attempted this centuries before, but the team in Baghdad, led by astronomers like Al-Khwarizmi and the Banu Musa brothers, designed a more sophisticated and extensive experiment. They didn't rely on a single measurement. Instead, they organized a full-scale expedition. One team traveled to a flat plain in northern Syria, while another remained in the Iraqi desert. At both locations, on the same day, they meticulously measured the angle of the sun at its highest point. By calculating the difference in these angles and then painstakingly measuring the actual distance between the two locations, they could apply trigonometric principles to determine the size of the Earth. Their result was astonishingly accurate, coming within a few hundred miles of the modern value. This was more than just a number. It was a bold declaration that the natural world could be understood through measurement and reason, and it demonstrated a global perspective that was centuries ahead of its time. The relentless collection of data led to the creation of a new genre of scientific literature, the Zij. These were comprehensive astronomical handbooks that combined star catalogs, planetary tables, and instructions for using various instruments. One of the most influential early works was the Zij al-Sindhind, compiled by a team of scholars including Al-Khwarizmi. This wasn't just a list of stars, it was a dynamic computational tool. It contained tables predicting the positions of the sun, moon, and planets for any given date, along with methods for calculating eclipses and visibility of the lunar crescent. These tables were constantly refined and updated as observations improved. Later, the work of astronomers like al-Battani, based in Raqqa, reached even greater levels of precision. His tables corrected errors in Ptolemy's data regarding the length of the solar year and the precession of the equinoxes, and his detailed records of solar and lunar eclipses provided a valuable data set for centuries of future astronomers. The Zij became the standard reference for anyone working in the field, from timekeepers in mosques to navigators on the Indian Ocean. This critical engagement with existing models inevitably led to challenges against the established order of the heavens. The Ptolemaic system, for all its mathematical elegance, was clunky and philosophically unsatisfying to many. Its use of an equant point, a technical device that violated the principle of uniform circular motion, was particularly troublesome. Scholars began proposing alternatives. In the 10th century, in the observatory at Baghdad, an astronomer named Al-Shani is reported to have suggested a radical idea. Perhaps the Earth itself rotates. While this heliocentric concept wouldn't be fully developed for another 600 years, the fact that it was being seriously debated in the halls of the House of Wisdom speaks volumes about the intellectual freedom and daring of the era. More systematically, astronomers like Ibn al-Haytham wrote scathing critiques of Ptolemy's models in his work Doubts Concerning Ptolemy, arguing for a physics that was consistent with the mathematics. This critical spirit, this refusal to accept authority without question, was the true legacy of Baghdadi astronomy. They were not just map makers of the sky, they were pioneers questioning the very nature of the map itself, setting the stage for the scientific revolutions that would eventually transform our understanding of the universe. Yet while the astronomers were mapping the cosmos, another group of scholars in Baghdad was focused on a much more intimate frontier, the human body itself. The field of medicine experienced a transformation just as profound, moving from theoretical knowledge to hands-on practice in a way that would define medical care for centuries. This advancement was built on the same foundation as everything else, the meticulous translation of Greek texts, especially the vast works of Galen. But the physicians of Baghdad were not content to be mere followers. They became pioneers, establishing a system of medical education, diagnosis, and treatment that integrated theory with rigorous clinical observation. The most powerful symbol of this new approach was the emergence of the hospital, or Beimer-Istan, which was far more than a place for the sick. It became the world's first true medical school and a center for groundbreaking innovation. The architect of this clinical revolution was a man named al-Razi, known in the West as Rhazes. Born in the mid-9th century, al-Razi was a true polymath, but his legacy in medicine is colossal. He served as the chief physician of the Baghdad hospital, and his approach was radically empirical. He insisted that a doctor must trust their own eyes and experience over the authority of any ancient text. This philosophy is brilliantly captured in his most famous work, the Comprehensive Book on Medicine, a monumental encyclopedia that synthesized knowledge from Greek, Persian, and Indian sources, but always filtered through the lens of his own practice. However, his masterpiece is arguably a smaller, more personal book called On Smallpox and Measles. In this text, he provides the first clear, clinical differentiation between the two diseases, describing their symptoms with a precision that was unprecedented. He didn't just list symptoms, he provided a diagnostic guide based on careful observation, noting the specific timing of rashes, the nature of fevers, and the subtleties that allowed a physician to tell them apart, a crucial skill that saved countless lives. Al-Razi's commitment to evidence-based medicine extended to his role as a teacher and hospital administrator. He is credited with introducing the use of medical rounds, where senior physicians would lead students from bed to bed, discussing cases and symptoms in real time. This transformed the hospital from a passive warehouse for the ill into an active classroom. He also championed the importance of the patient's environment and mental state in healing, a holistic view that feels remarkably modern. His diagnostic methods were systematic. He wrote extensively on the importance of taking a detailed patient history and using all the senses, not just sight, but touch, sound, and even smell to arrive at an accurate conclusion. Al-Razi's legacy was one of relentless curiosity and skepticism. He even wrote a fascinating book titled Doubts about Galen, where he courageously pointed out errors in the work of the revered Greek master, proving that even the greatest authorities were subject to question and improvement through practical experience. If al-Razi was the master clinician, then Ibn Sina, or Avicenna, was the grand theorist who sought to systematize all of medical knowledge. A generation younger, Ibn Sina was a prodigy who wrote his monumental The Canon of Medicine while still a young man. This 5-volume work is perhaps the most influential medical textbook ever written. For over 6 centuries, it served as the primary guide for physicians in both the Islamic world and Europe, where it was translated into Latin and became a standard text in universities. The genius of the canon was its breathtaking organization. Ibn Sina didn't just collect facts, he created a logical, comprehensive structure for the entire field of medicine. It began with fundamental principles of anatomy and physiology, drawn from Galen but refined, then moved systematically through the causes and symptoms of diseases, covered maintaining health through diet and lifestyle, detailed the use of specific medications, and finally explained complex surgical procedures. The canon's enduring power lay in its methodical approach and its integration of philosophy with practical medicine. Ibn Sina applied Aristotelian logic to diagnosis, creating a system that was both teachable and reliable. He accurately described the contagious nature of certain diseases, the workings of the nervous system, and the effects of the environment on health. He cataloged hundreds of drugs and their uses, and his descriptions of conditions like depression and anxiety showed a deep understanding of the connection between mind and body. While some of his theories, like the 4 humors, were inherited from the Greeks, the sheer scope and clarity of the canon made it an indispensable reference. It became the ultimate medical authority, a single source that a physician anywhere from Spain to India could consult for guidance on everything from a common fever to a complicated fracture. Its translation into Latin helped to pull European medicine out of the Dark Ages, providing a structured body of knowledge that would underpin Western medical training for hundreds of years. The theories of these great minds, however, were put into practice within an institution that was a marvel of its time, the public hospital. The Baymaristan was a uniquely Islamic contribution to civilization, and Baghdad was home to some of the largest and most advanced. Funded by charitable endowments, these hospitals were open to everyone, rich and poor, Muslim and non-Muslim, free of charge. They were designed with a shocking degree of sophistication, featuring separate wards for different diseases, a crucial innovation for preventing the spread of infection, as well as libraries, pharmacies, and lecture halls for teaching. The most famous, the Al-Adudi Hospital, built in the 10th century, was said to have employed 25 physicians and housed a vast array of medical specialists, from surgeons and orthoptists to ophthalmologists and psychiatrists. It was within these walls that medical students received their training, moving from studying texts like the canon to applying that knowledge under the supervision of experienced doctors. This combination of rigorous book learning and mandatory clinical apprenticeship created a standard of medical competence that was unmatched. The hospitals also served as research centers. Physicians kept detailed patient records, tracking the progression of illnesses and the effectiveness of treatments, which allowed them to refine their methods continuously. This environment fostered incredible specialization. Surgeons developed new techniques for cataract removal and hernia repairs, while ophthalmologists wrote detailed manuals on eye diseases. Pharmacists, working in the hospital's own laboratory, the Saydalani, compounded complex medicines from hundreds of herbal and mineral ingredients, creating standardized formulas and testing their potency. The hospital was the living, breathing embodiment of the Islamic Golden Age's ethos. Knowledge was not to be locked away in books, but was meant to be applied for the betterment of all humanity, creating a system of compassionate, scientific, and accessible health care that would not be seen again on such a scale for centuries. But beyond the stars and the scalpel, in the quieter halls of the House of Wisdom, a different kind of exploration was underway, one that grappled with the most fundamental questions of existence, knowledge, and the divine. The scholars of Baghdad were not just scientists and doctors. They were deep philosophical thinkers who engaged in a spirited and centuries-long conversation with the giants of Greek thought. The arrival of the complete works of Plato and Aristotle, translated into Arabic, was like an intellectual earthquake. It presented a comprehensive system of logic, metaphysics, and ethics that was both dazzling and, at times, deeply challenging to the prevailing Islamic worldview. This wasn't a simple adoption of foreign ideas. It was a creative and often tense encounter, a fusion of reason and revelation that gave birth to entirely new schools of philosophical inquiry. At the heart of this movement was a discipline known as Kalam, or Islamic scholastic theology. The practitioners of Kalam, called Mutakallamun, were primarily concerned with defending and explaining Islamic doctrine using rational argumentation. When they encountered Greek philosophy, particularly the logical tools of Aristotle, they saw a powerful new weapon. They began employing Aristotelian logic to debate complex theological issues, such as the nature of God's attributes, the concept of free will versus predestination, and the creation of the universe. This created a fascinating dynamic. Think of it as a dialogue between two different ways of knowing, one rooted in the certainty of divine text, and the other in the power of human reason. The Mutakallamun weren't trying to replace faith with philosophy. They were attempting to show that reason, properly guided, could lead to a deeper appreciation and defense of religious truth. This project reached its zenith with the rise of the Mutazilite school, which enjoyed the official support of Caliph Al-Mamun himself. The Mutazila were rationalists to their core. They championed the idea that ethical truths could be discerned through reason alone, even without revelation, and they insisted on a strictly rational, unified conception of God that avoided any anthropomorphic language. Their most famous and controversial doctrine was the belief that the Quran, as the speech of God, was created in time, rather than being eternal and uncreated like God himself. This was a radical attempt to protect God's absolute oneness from any association, even with his own speech. To enforce this view, Al-Mamun instituted a brief but intense period of inquisition known as the Mitna, testing the beliefs of scholars and judges. This episode highlights the high stakes of these philosophical debates. They were not merely academic, but had profound implications for political power and religious orthodoxy. Inevitably, a powerful reaction arose against the dominance of Greek-inspired rationalism. This counter-movement was led by the towering figure of Abu Hamid al-Ghazali, a scholar of the 11th century. In his seminal work, The Incoherence of the Philosophers, al-Ghazali launched a devastating critique against the Islamic philosophers who, in his view, had blindly followed Aristotle into heresy. He specifically targeted thinkers like al-Farabi and Ibn Sina for their beliefs in the eternity of the world and their denial of bodily resurrection, arguing that these ideas were logically incoherent and contradicted core Islamic teachings. Al-Ghazali's brilliance was not in rejecting reason outright, but in demonstrating its limits. He argued that while logic was useful in many fields, it was incapable of providing certain knowledge about metaphysical realities like God and the soul. True certainty, he contended, came not from syllogisms but from direct mystical experience and the light of divine inspiration. Yet, the philosophical tradition was resilient. A direct response to al-Ghazali came from the Andalusian philosopher Ibn Rushd, known in the West as Averroes. In his book The Incoherence of the Incoherence, Ibn Rushd defended the role of philosophy, arguing that demonstrative truth reached through reason and the truth of revelation could not ultimately conflict. He proposed a sophisticated theory of multiple levels of truth, suggesting that the same fundamental reality could be expressed in the symbolic language of religion for the masses and the abstract language of philosophy for the intellectual elite. This idea of double truth would become highly influential in medieval Europe. The debate between these giants of the rigorous rationalism of the Mu'tazila, the spiritual critique of al-Ghazali, and the sophisticated harmonization of Ibn Rushd defined the rich and complex landscape of Islamic philosophy. It was a testament to the intellectual maturity of the age that such profound disagreements could be aired and debated with such logical rigor, creating a legacy of philosophical inquiry that would deeply influence the subsequent course of thought in both the East and the West. Yet alongside the grand theories of the cosmos and the human body, another, more hands-on discipline was flourishing in the workshops of Baghdad, one that sought to unlock the hidden properties of matter itself. This was the world of alchemy, a field often misunderstood today as mere mystical questing for gold. For the scholars of the Islamic Golden Age, however, alchemy represented a serious and systematic experimental science, the direct precursor to modern chemistry. It was driven by a powerful philosophical idea that the materials of the earth were not fixed and immutable, but could be transformed through precise, controlled processes. This quest for transformation was as much about understanding the fundamental nature of reality as it was about any practical outcome, and its greatest pioneer was a figure whose legendary status is matched by his practical genius, Jabir ibn Hayyan. Working in the late 8th and early 9th centuries, Jabir, known in the West as Geber, was a man firmly rooted in the empirical spirit of the House of Wisdom. What set him apart was his unshakable belief in the necessity of experiment. He famously argued that the only path to true knowledge was through direct, hands-on work in the laboratory, dismissing those who relied solely on book learning. His voluminous writings, which form an entire encyclopedia of alchemical knowledge, are filled with meticulous descriptions of apparatus, step-by-step procedures, and, most importantly, records of his failures. This commitment to documenting the entire experimental process, successes and setbacks alike, marks a crucial step in the development of the scientific method. Jabir wasn't just following recipes, he was testing hypotheses, varying conditions, and carefully observing the results, building a body of practical knowledge based on reproducible evidence. His most enduring contribution was the development and refinement of fundamental chemical processes that are still in use today. Foremost among these was distillation. While simple distillation was known to earlier cultures, Jabir and his followers perfected the apparatus, designing and describing the alembic, or alembic, in intricate detail. This device, typically made of glass or ceramic, consisted of a boiling vessel connected by a tube to a cooling chamber where vapors would condense back into liquid. With this tool, They could separate mixtures based on differences in boiling points. They used it to produce concentrated acids, like nitric acid and sulfuric acid, by distilling various mineral salts. They also isolated pure alcohol, which they called al-Kohl, initially for medicinal and perfumery purposes. This ability to purify and concentrate substances opened up entirely new possibilities, allowing them to study the properties of matter in its most fundamental forms. But Jabir's work went far beyond a single technique. His laboratories were equipped with an entire toolkit of specialized equipment that would look familiar to any modern chemist. He described the use of furnaces capable of maintaining specific temperatures for long periods, essential for processes like calcination, the heating of a substance to a high temperature to cause decomposition. He detailed the use of crucibles, beakers, flasks, and filtration systems. He developed methods for crystallization, sublimation, the transformation of a solid directly into a gas, and dissolution. Each piece of equipment was designed to exert a new kind of control over matter, to subject it to specific conditions of heat, pressure, or purification that would reveal its hidden qualities. This systematic approach to laboratory design transformed alchemy from a speculative art into a rigorous experimental science. Underpinning all this practical work was a sophisticated theoretical framework. Jabir and his successors developed the mercury-sulfur theory of metals, which proposed that all metals were composed of varying proportions of philosophical mercury and philosophical sulfur. These were not the common elements we think of today, but rather idealized principles. Mercury represented the metallic, shiny, and fusible quality, while sulfur represented the combustible, changeable aspect. The goal of the alchemist's art was to find the elusive substance, the al-Iksir or philosopher's stone, that could perfectly balance these principles within a base metal like lead, thereby transforming it into silver or gold. While this ultimate goal was never realized, the pursuit led to countless accidental discoveries. In their attempts to create the perfect catalyst, they discovered new compounds, observed startling chemical reactions, and developed a language for describing chemical change that emphasized proportion, reaction, and transformation. The legacy of these alchemical pioneers is immense. They established the laboratory as a dedicated space for scientific inquiry. They invented and standardized the core equipment that would be used by chemists for the next millennium. Most importantly, they instilled a mindset that valued meticulous observation and experimental proof over philosophical speculation. The processes they perfected, especially distillation, became the foundation not only for chemistry but for countless industries, from perfumery and pharmacology to metallurgy and the production of inks and dyes. The work that began in the fiery furnaces of Jabir ibn Hayyan's workshop was a crucial bridge, transforming the mystical art of alchemy into the rational science of chemistry, a discipline built on the conviction that by carefully manipulating the material world, we can uncover the profound secrets it holds. Of course, the drive to understand the world extended far beyond the motions of the planets and into the very contours of the Earth itself. While astronomers charted the heavens, another group of scholars in Baghdad was engaged in an equally ambitious project, mapping the known world with a level of accuracy and detail that was unprecedented. This was the science of geography, or ilm al-ma'alim, and it was fueled by the same intellectual energy that powered the House of Wisdom. The Abbasid Empire was a colossal network of trade routes stretching from the Atlantic coast of Africa to the borders of China. Information flowed into Baghdad along the Silk Road and the Indian Ocean trade routes, carried by merchants, diplomats, and travelers. These individuals became the unwitting field agents of geography, their first-hand accounts providing a torrent of raw data about distant lands, their climates, peoples, and customs. The scholars of Baghdad recognized that this information was a treasure trove, but it was also fragmented and often contradictory. Their great task was to sift through these travelers' tales, compare them, verify them when possible, and synthesize them into a coherent picture of the entire inhabited world. The first major attempt to systematize this new geographical knowledge came from a familiar genius, Muhammad al-Khwarizmi, Just as he had revolutionized mathematics, he now turned his analytical mind to the errors in the most authoritative world map of the ancient world, the geography of Ptolemy. Ptolemy's work, written in the 2nd century, was a magnificent achievement, but it contained significant mistakes, particularly about regions far from the Mediterranean. Al-Khwarizmi and his team at the House of Wisdom undertook a massive project to correct it. The result was his Kitab Surat al-Ard, or the Book of the Description of the Earth. This was not merely a book of stories, it was a technical masterpiece. It contained meticulously corrected coordinates for over 2,400 locations, cities, mountains, rivers, and coastlines plotted on a grid of longitude and latitude. He dramatically improved the map of Africa, correctly showing the Indian Ocean as open water, not a landlocked sea as Ptolemy had thought. He provided a far more accurate depiction of the Mediterranean's length and corrected the course of the Nile. Al-Khwarizmi's work represented a fundamental shift from relying on classical authority to trusting in empirical data gathered from contemporary sources, marking the birth of a truly scientific Islamic geography. This scientific approach soon blossomed into a rich tradition of geographical literature that went far beyond dry coordinates. Scholars began producing works known as al-Mazalik wa al-Mamalik, or the Routes and Realms. These were comprehensive geographical encyclopedias that combined hard cartographic data with vibrant descriptions of the cultures, economies, and histories of every province in the empire and the lands beyond. Think of them as part travel guide, part administrative manual, and part anthropological study. They provided a ruler in Baghdad with crucial knowledge about the wealth and resources of a distant province, and they offered a merchant vital information about the safe routes and markets of a foreign land. This genre reached its peak with the work of geographers like al-Muqaddasi in the 10th century, who famously traveled throughout the Islamic world himself, critically observing and comparing regions with a sharp eye for detail. He didn't just report what he heard. He developed a methodology for evaluating the reliability of his sources, creating a layered understanding of the world that was both quantitative and qualitative. Out of this flourishing tradition emerged a distinct and influential school of cartography in the 10th century, often referred to as the Balkhi school, named after its founder, Abu Zayd al-Balkhi. While al-Khwarizmi's maps were heavily influenced by the mathematical Ptolemaic tradition, the Balkhi school represented a different, equally important approach. Their focus was less on precise mathematical projection and more on creating what we might call human geography. The maps produced by this school, and by later masters like al-Istakari and Ibn Hawqal, were designed to be practical and illustrative. They were often schematic, using clear, almost diagrammatic lines to show the interconnectedness of trade routes, rivers, and major cities within the Islamic world. The world was typically depicted with south at the top, and the maps were richly annotated with information about agricultural products, cultural practices, and political boundaries. The real innovation of the Balkhi school was its concept of regional geography. Instead of producing one single world map, they created a series of maps, each dedicated to a specific province or major region, a map of Persia, a map of the Maghreb, a map of Egypt, and so on. This allowed for a much greater level of local detail. A merchant planning a journey from Baghdad to Bukhara could consult the specific map for the Khorasan region and see not only the main roads, but also the locations of caravanserais, sources of water, and potential hazards. These maps were circulated in beautifully illustrated atlases, making geographical knowledge accessible to a much wider audience beyond the court astronomers. This pragmatic, user-centered approach to cartography ensured that the scholarly work of geographers in Baghdad had a direct and tangible impact on the economic and cultural life of the empire, literally putting the world on a map that anyone could understand and use. While the astronomers and chemists were building a new understanding of the natural world, another group of scholars in Baghdad was engaged in a different but equally vital quest, the urgent task of preserving memory itself. For the burgeoning Islamic empire, history was not a mere academic curiosity, It was a matter of existential importance. The community needed to understand its own rapid transformation from a small group of believers in the Arabian desert to the rulers of a vast, multicultural civilization. How did this happen? What were the lessons of the past, both for governing justly and for understanding God's plan for humanity? This pressing need to document, interpret, and learn from the past gave rise to a sophisticated tradition of historiography that went far beyond simple chronicling, producing works of breathtaking scope and critical analysis that remain foundational to this day. The early Muslim historians faced a monumental challenge. The primary sources for the life of the Prophet Muhammad and the early caliphs were not neatly archived in libraries. They were scattered in the memories of thousands of individuals across the empire, passed down as oral reports known as hadith and akbar. The first historical methodology, therefore, was born from the science of verifying these reports. Scholars would travel vast distances to collect accounts from reliable transmitters, meticulously checking the integrity of each person in the chain of narration, or isnad. They asked critical questions. Was this person known to be truthful? Could they have physically been in the place and time to witness the event they described? Were there contradictory reports? This rigorous method, known as ilm al-rijal, the science of men, was developed to establish the authenticity of religious traditions, but historians soon applied the same painstaking criteria to secular and political history. This insistence on sourcing and verification was a revolutionary approach, establishing a proto-scientific standard for historical truth that prioritized evidence over legend. This methodology reached its absolute pinnacle in the work of Abu Ja'far al-Tabari, a scholar of the 9th and 10th centuries whose History of the Prophets and Kings, often called Tariq al-Tabari, is arguably the single most important work of Islamic history ever written. To call it comprehensive would be a profound understatement. Al-Tabari's history begins with the creation of the world according to Islamic tradition and marches forward in an annual chronicle, year by painstaking year, right up to the year 915. His method was one of remarkable intellectual honesty and compilation. He did not simply write a single smooth narrative. Instead, he presented multiple, often conflicting accounts of the same event, each preceded by its full chain of transmitters. He would then, occasionally, offer his own brief judgment on which version he found most reliable. This approach transformed his work from a mere history book into a vast, open-source database of the early Islamic world. A reader is not given a single authoritative story of, for instance, the assassination of the Caliph Uthman. They are presented with half a dozen different perspectives, allowing them to see the event through the eyes of various factions and witnesses. This created a complex, multi-dimensional understanding of the past, acknowledging that history is rarely a simple story with one clear truth. The sheer scale of al-Tabari's project is almost unimaginable. It is said that he wrote 40 pages every day for 40 years. His history draws from an immense variety of sources: earlier Arab chronicles, Persian royal histories, Syriac Christian texts, Jewish traditions, and the vast corpus of oral reports he himself collected. He wove these threads together into a coherent chronology that placed the history of the Islamic Empire within the broader context of world history, linking it to the stories of the biblical prophets, the kings of ancient Persia, and the emperors of Rome. For historians today, Tariq al-Tabari is an indispensable treasure trove. It preserves thousands of documents, speeches, and poems that would have otherwise been lost forever. It provides the foundational narrative for the first 3 centuries of Islam, and because of his method of citing sources, it allows modern scholars to deconstruct his narrative, to trace the biases of his informants, and to understand how historical memory was shaped and contested in the formative period of the empire. But the study of history in Baghdad was not limited to the Islamic era. The scholars displayed a deep and genuine curiosity about the civilizations that had come before. The same translation movement that brought Greek science to Baghdad also made available the historical works of other cultures. They translated the great Persian epic, the Kahwate-Namag, the Book of Lords, which told the history of the Sasanian Empire. They studied the histories of the Byzantines and delved into the lore of ancient India. This was more than antiquarianism. It was a conscious effort to understand the full sweep of human civilization and to locate the new Islamic empire within that grand timeline. They recognized patterns of rise and fall, lessons about justice and tyranny, and the cultural achievements of past societies. This broad, cosmopolitan view of history fostered a sense of continuity, positioning Islamic civilization not as a break from the past, but as the inheritor and synthesizer of all world history, responsible for preserving its legacy and advancing its achievements for future generations. This remarkable intellectual energy, spanning from the stars to the soul, found a parallel and equally vital expression in a discipline that was uniquely central to the Islamic world: the formal study of language itself. While other civilizations had grammarians, the scholars of Baghdad undertook a project of linguistic analysis so systematic and profound that it would shape the very identity of their civilization for a millennium. The impetus was both practical and sacred. As the Abbasid Empire expanded, incorporating millions of non-Arab converts into the fold of Islam, a pressing problem emerged. Classical Arabic, the language of the Quran, was at risk of being corrupted by the colloquial dialects of new Muslims and the influence of other languages like Persian and Aramaic. For a faith where the divine revelation was believed to be inextricably linked to the precise wording of its holy text, this was not a trivial matter. A mispronounced vowel or a misconstrued grammatical rule could, in theory, alter the meaning of a Quranic verse, with profound theological consequences. The survival of the faith in its pure form depended on the preservation of its language. This urgent need sparked a golden age of linguistics and philology, turning the study of Arabic into a rigorous science. The birthplace of this science was not Baghdad initially, but the garrison cities of Basra and Kufa in Iraq, where rival schools of grammarians emerged in the 8th century, engaging in fierce and brilliant debates. The most legendary figure from this formative period was a Persian scholar from Basra named Sibawayh. His monumental work, simply known as Al-Kitab, or the Book, is arguably one of the most influential books ever written on any language. It was not a simple grammar guide. It was a complete and systematic theory of the Arabic language, analyzing its sounds, its word formations, and its sentence structures with a logical rigor that would not be seen in the West for centuries. Sibawayh approached Arabic not as a set of rigid rules to be memorized, but as a coherent, living system to be understood. He was a master of phonetics, describing with astonishing accuracy the exact points of articulation in the mouth and throat for each Arabic letter, from the deep guttural sounds to the delicate dental consonants. He developed a sophisticated theory of grammatical governance, explaining how certain words dictate the case endings of others in a sentence, creating a logical dependency tree long before modern linguistics. The scholars of these early schools were essentially linguistic detectives, and their primary source of evidence was the vast corpus of pre-Islamic poetry. They would travel deep into the Arabian desert to interview Bedouin tribes, who were considered the preservers of the purest, most uncorrupted form of Arabic. They collected thousands of lines of poetry, proverbs, and oral narratives, treating these texts as a linguistic database. When a grammatical rule was in dispute, they would scour this corpus for an authentic line of poetry that could serve as definitive proof. This empirical method, relying on documented usage rather than abstract logic, mirrored the observational approach developing in the sciences. The rivalry between the Basran and Kufan schools was intense, with each side critiquing the other's analyses and championing their own interpretations. This competitive environment, much like the debates among astronomers or physicians, drove the science of language to ever greater levels of sophistication and precision. By the time the center of intellectual gravity shifted to Baghdad, the foundational work was complete, ready to be institutionalized and expanded within the city's great academies. As the language was being systematically mapped by its grammarians, a parallel and equally ambitious project was underway: the task of cataloging its entire vocabulary. The Arabic language, with its rich root-based system where thousands of words can spring from a single three-letter core, presented a unique challenge for lexicographers. How do you organize a dictionary for such a language? The solution, pioneered by scholars like Al-Khalil ibn Ahmad al-Farahidi in the 8th century, was a work of genius. Al-Khalil devised the first dictionary of the Arabic language, the Kitab al-Ain, organized not by the first letter of a word, as we do today, but by its phonetic properties. He arranged the letters based on where they were produced in the mouth, starting from the deepest throat sound, the Ain, which gave the dictionary its name. This was a system created by a true scientist of language, but his most lasting contribution was the concept of organizing words by their root letters. He systematically listed every possible permutation of the Arabic radicals, grouping together all words derived from the same root. This meant that in Al-Khalil's dictionary, you would find the words for book, writer, library, and inscription all listed under the same root, KTB, revealing the deep conceptual connections within the language and providing an incredibly powerful tool for poets, scholars, and theologians alike. This scholarly fervor for language did not exist in an ivory tower. It infused the very air of Baghdad's cultural life. The city's salons, known as majalis, became vibrant hubs where poets, grammarians, and patrons would gather for spirited competitions. A poet would recite a new composition, and the assembled scholars would dissect its language, praising its adherence to classical norms or critiquing a perceived grammatical flaw. This created an environment where linguistic excellence was not just an academic pursuit, but a marker of social status and intellectual refinement. The caliphs themselves were active participants, often acting as patrons and judges in these literary contests. This deep integration of linguistic science with high culture ensured that the sophisticated theories developed by scholars like Sibawayh had a direct and immediate impact on the living art of literature. It fostered a style of poetry that was both intensely creative and meticulously crafted, valued for its aesthetic beauty and its grammatical purity. The study of language was, therefore, a unifying force, connecting the sacred text of the Quran with the highest expressions of secular art, and binding together the diverse members of the elite through a shared commitment to the power and precision of the Arabic word. But for all the grand theories about the cosmos and the human soul, for all the poetic beauty of the language and the meticulous records of history, this vibrant civilization needed a practical framework to function day by day. How should a society, composed of people from dozens of different cultures and backgrounds, govern itself? What rules should guide commerce, resolve disputes, and define the relationship between the individual, the community, and the state? The answer to these fundamental questions was found not in a king's decree, but in a sophisticated and dynamic science that became the bedrock of daily life, Islamic law, or fiqh. More than just a set of rigid commandments, fiqh was a living, breathing intellectual discipline, a constantly evolving conversation about justice, ethics, and the divine will, and its development was one of the most profound achievements of the scholars in Baghdad. The very word fiqh means deep understanding or comprehension, and that is precisely what it entailed. It was not about blindly following rules, but about cultivating a profound understanding of the principles behind them. The primary sources for this law were twofold. First, and most sacred, was the Quran, believed by Muslims to be the literal, unchanging word of God. Second were the Hadith, the vast collections of reported sayings, actions, and approvals of the Prophet Muhammad, which served as a living example of how to implement the Quran's guidance. But these sources, while comprehensive in spirit, did not contain a specific answer for every single situation that could arise in a sprawling, cosmopolitan empire. The Quran might set broad principles for fair trade, but it didn't specify the legal intricacies of a complex partnership contract between a Persian merchant and an Iraqi investor. The Hadith might describe the Prophet's personal hygiene, but it didn't address the novel medical procedures being developed in Baghdad's hospitals, This gap between the eternal sources and the ever-changing realities of life is where the real work of fiqh began. To bridge this gap, the scholars of law developed a sophisticated methodology known as usul al-fiqh, the roots of jurisprudence. This was the legal engine of the civilization, a systematic process for deriving new laws. The first step was always to search the Quran and the authenticated hadith for a direct ruling. If a clear text was found, that was the end of the matter. But if no direct answer existed, the jurist would then employ reasoned interpretation. The most important tool was qiyas, or analogical reasoning. A jurist would identify the underlying cause, or illah, of a known ruling and apply it to a new situation that shared the same cause. For example, if the Quran prohibited wine because it intoxicates, then by qiyas, any substance that causes intoxication, whether made from grapes, dates, or grains, would also be prohibited, because the effective cause was the same. This allowed the law to remain relevant and adaptable to new circumstances without sacrificing its core principles. Beyond qiyas, jurists also relied on ijma, or consensus. If the learned scholars of a particular generation reached a unanimous agreement on a legal issue, that consensus was considered a binding source of law, based on the idea that the community as a whole would not agree on an error. Another key principle was ijtihad, which means independent reasoning, or intellectual striving. A qualified jurist, known as a mujtahid, would exert his utmost effort to arrive at a legal opinion when the primary sources were silent or ambiguous. This was not a free-for-all. It was a disciplined process bound by the strict rules of usul al-fiqh. The ultimate goal of this entire methodology was not to create burdens, but to identify what God desired for humanity in any given situation, to discern the path that would lead to benefit and repel harm. This pursuit was seen as a form of worship, and the scholars who dedicated their lives to it were held in the highest esteem. Over time, as the empire grew, and these legal methodologies were applied by different master jurists in different regions, distinct schools of legal thought began to crystallize. These schools, known as madhahib singular madhab, were not sects but rather different interpretive traditions, each with its own slight variations in methodology and emphasis. In Baghdad, two schools became particularly prominent and influential, reflecting the city's role as a crossroads of intellectual debate. The first was the Hanafi school, founded by Abu Hanifa in the 8th century in Kufa, which heavily emphasized the use of reasoned opinion, ray, and qiyas. The Hanafi approach was known for its flexibility and its consideration of public interest, making it well suited for the complex commercial and social life of a major metropolis like Baghdad. It was often the preferred school of the Abbasid rulers for administering justice. The second major school was the Hanbali school, founded by Ahmad ibn Hanbal, who lived and taught in Baghdad itself. Ibn Hanbal's approach was far more cautious, prioritizing the literal text of the Quran and Hadith above all else, and being very wary of analogical reasoning if it seemed to stray too far from the original texts. His school represented a more traditionalist, scripturalist strand of thought, and his steadfastness in the face of the Mitna Inquisition made him a revered figure of integrity. The simultaneous presence of these two schools, one more flexible and rationalist, the other more textually conservative, created a vibrant legal landscape in the city. A citizen of Baghdad could, in theory, seek a legal opinion from a scholar of either tradition, and the differences between them on specific issues were debated in public forums, ensuring that the law remained a subject of lively public discourse rather than a monolithic imposition from the state. These scholars were not isolated academics, they were integral pillars of society, serving as judges, cadis, legal advisors, muftis, and teachers. A cadi was a state-appointed judge who presided over courts, hearing cases ranging from commercial disputes and family matters to criminal accusations. His role was to apply the principles of fiqh to deliver a binding verdict. The position required not only deep legal knowledge, but also a reputation for impeccable character and impartiality. Then there was the mufti, an independent scholar who issued non-binding legal opinions, or fatwas, in response to questions from individuals or the government. A fatwa was not a court order, it was a learned opinion explaining what the law was on a particular matter. This system created a healthy separation between the scholarly interpretation of the law and the state's application of it, allowing for a diversity of opinions to flourish without paralyzing the judicial system. The influence of these legal scholars extended into every corner of life. Their opinions shaped business law, ensuring contracts were fair and disputes could be resolved justly, which was essential for Baghdad's thriving economy. They developed intricate laws of inheritance that guaranteed the financial rights of women and minors long before such concepts existed elsewhere. They deliberated on the ethical guidelines for medical practice, the rules of warfare, and the environmental regulations concerning water rights in public spaces. The development of fiqh was a monumental achievement in creating a rule of law society. It demonstrated that divine guidance, when approached with deep understanding, rigorous methodology, and intellectual humility, could provide a comprehensive framework for a complex and diverse civilization to live together in justice and order, a framework that was debated, refined, and lived out daily on the bustling streets of Baghdad. This intellectual energy, however, was not confined to the material world or the halls of law. It soared into the most profound and challenging realm of all, the nature of God, the universe, and human destiny. This was the domain of theology, known as kalam, a term that literally means speech or discourse. But kalam was far more than just talk. It was a rigorous intellectual discipline, a form of scholastic theology where scholars, known as mutakalimun, used logical argumentation to defend and articulate Islamic doctrine. The arrival of Greek philosophy, with its powerful tools of logic and metaphysics from Plato and Aristotle, acted like a seismic event for these thinkers. It presented a comprehensive system for understanding reality through pure reason, a system that was both awe-inspiring and, in some ways, deeply challenging to the truths received through revelation. The scholars of Baghdad did not shy away from this challenge. Instead, they engaged in a centuries-long, spirited conversation that would define Islamic thought, giving rise to fierce debates and brilliant syntheses. At the forefront of this rationalist movement were the Mu'tazilites, a school of thought that came to prominence in the early 9th century and even enjoyed the official patronage of Caliph Al-Mansur himself. The Mu'tazila were, in essence, the rationalists of their age. They championed the power of human intellect, arguing that reason was a God-given faculty that could independently discern ethical truths, that we could know good from evil through logic, even without the guidance of revelation. This belief led them to their most famous and controversial principle, the createdness of the Quran. They argued that the Quran, as the speech of God, must have been created in time. To them, the alternative that the Quran was eternal and uncreated, like God himself, seemed to compromise the absolute, uncompromising oneness of God, or Tawhid. If there were two eternal things, God and his speech, then in their view, that hinted at a form of polytheism. This was not a minor philosophical point. It was a radical attempt to protect the purity of divine unity through rational consistency. Their rationalism also fueled a passionate defense of human free will, a stance that placed them in direct opposition to more predestinarian views. The Mu'tazilites argued that if God is just, as the Quran constantly affirms, then humans must possess genuine moral agency. How could a just God hold people accountable for their actions on the day of judgment if those actions were preordained by him? They believed that God creates the capacity for action within humans, but it is the individual who freely chooses to perform the act. This belief in human responsibility made justice a cornerstone of their theology, not just as a divine attribute, but as an objective reality that even God himself, in their view, was bound to uphold. This emphasis on reason, justice, and God's unity made Mu'tazilism an intellectually powerful and appealing system. But its abstract nature and its official enforcement during the Mitna Inquisition also created significant opposition. That opposition found its most formidable voice in the figure of Abu al-Hasan al-Ash'ari. Originally a Mu'tazilite himself, Al-Ash'ari reportedly experienced a profound change of heart and went on to found the Ash'ari school, which would become one of the most dominant theological positions in Sunni Islam. Al-Ash'ari's genius lay in his ability to use the Mu'tazilites' own logical weapons against them, while steering theology back toward a greater emphasis on the authority of revelation. On the issue of the Quran, he argued for its eternal nature as the uncreated speech of God, a belief that resonated more deeply with the mainstream understanding of the Quran's divine origin. But his most sophisticated contribution was his solution to the free will dilemma, a concept known as kasb, or acquisition. Al-Ash'ari proposed a middle path. He agreed that God is the ultimate creator of all acts, upholding divine omnipotence. However, he argued that God creates the act and the human capacity for it simultaneously, and the human acquires the act, making it their own through a kind of intentional alignment with it. This complex theory attempted to reconcile absolute divine power with a form of human responsibility that was sufficient for God's justice to be meaningful. The debate between these schools was not confined to dusty libraries. It reverberated through the entire culture, engaging philosophers who sought to build even more comprehensive systems. Thinkers like Al-Farabi and Ibn Sina integrated Neoplatonic ideas into their worldview, envisioning a universe that emanated from God through a series of necessary intermediaries. This philosophical approach often led to conclusions that clashed with orthodox belief, such as the idea of the world's eternity. The tension between pure philosophy and revealed religion reached a dramatic climax with the work of Abu Hamid al-Ghazali, a scholar of the 11th century. In his devastating critique, The Incoherence of the Philosophers, Al-Ghazali argued that philosophers like Ibn Sina had overstepped the bounds of reason, falling into logical contradictions and outright heresy on matters like the resurrection of the body. Al-Ghazali did not reject reason entirely. He masterfully demonstrated its limits, arguing that certain truths about God and the soul could only be grasped through direct experience and the inner light of faith. This rich tapestry of theological debate, weaving together reason and revelation, justice and divine power, demonstrated the incredible intellectual maturity of the era. It was a world where the biggest questions were not suppressed, but were openly and rigorously debated, where the tools of logic were honed in the service of understanding the divine. This conversation did not end in Baghdad. It would travel west to Spain, where Ibn Rushd, known as Averroes, would write a famous rebuttal to Al-Ghazali, and its echoes would profoundly influence the development of Jewish and Christian scholasticism in medieval Europe. The work of the Mutakallimun ensured that faith was not a simple matter of blind obedience, but a dynamic, intellectually vibrant pursuit of truth. The same relentless curiosity that drove the scholars of Baghdad to chart the heavens and delve into the human body also compelled them to understand the invisible forces that govern the world right before their eyes. While philosophers debated the nature of reality, a different group of thinkers was asking profoundly practical questions. How does light travel? What are the principles that allow a great lever to lift a massive weight? How can the power of flowing water be harnessed not just for irrigation, but to measure the passage of time itself? This was the world of physics and engineering, where abstract principles were tested, refined, and transformed into tangible marvels that pushed the boundaries of what was thought possible. And in this field, one man's revolutionary work on the nature of sight would fundamentally change our understanding of light and vision forever, laying the groundwork for everything from modern optics to the scientific method itself. That man was Abu Ali al-Hasan ibn al-Haytham, known in the West as al-Hazan. Ibn al-Haytham's journey to Baghdad is a story in itself. Born in Basra in the 10th century, his intellectual reputation was so great that he was invited to Egypt by the Fatimid Caliph al-Hakim with a seemingly impossible task: to regulate the flooding of the Nile. When Ibn al-Haytham realized the scale of the challenge was beyond the engineering capabilities of his time, he feared the caliph's wrath. To escape, he feigned madness, a ruse that forced him into house arrest for years. Yet, This period of enforced isolation became one of the most productive in scientific history. Freed from other duties, he devoted himself entirely to research, reading, and writing. It was during this time that he composed his monumental work, the Book of Optics, or Kitab al-Manazir, a 7-volume masterpiece that would completely overturn 1,000 years of accepted wisdom about how we see. For centuries, the dominant theory of vision in Europe and the Islamic world was the emission theory, championed by Greek thinkers like Euclid and Ptolemy. They believed that the eye itself emitted a kind of visual ray that traveled outward, scanned objects, and then returned to the eye with their image. Ibn al-Haytham, through a series of brilliant and simple experiments, proved this was wrong. He argued convincingly for the intromission theory, that vision occurs when light rays, originating from a source like the sun or a lamp, bounce off objects and then travel into the eye. To prove his point, he considered the experience of being blinded by looking directly at the sun. If the eye emitted light, he reasoned, why would looking at a bright light cause pain and damage? His own theory explained it perfectly. The intense light entering the eye was simply too powerful. But Ibn al-Haytham was not content with a general theory. He delved into the precise mechanics of light's behavior, exploring phenomena that we now explain with the laws of reflection and refraction. He conducted experiments with dark chambers, which would later be called camera obscuras. He noted that light travels in straight lines and described how these rays form an inverted image when they pass through a small pinhole into a dark room. He studied the properties of mirrors, flat, spherical, and parabolic, detailing the angles of reflection with geometric precision. He also investigated refraction, the bending of light as it passes from one medium to another, like from air into water or glass. While he didn't discover the exact mathematical law that Snell would later formulate, he accurately described the phenomenon and constructed lenses that could magnify objects, laying the foundational work for the eventual invention of eyeglasses, telescopes, and microscopes. Perhaps his most enduring legacy, however, was his methodology. Ibn al-Haytham is often called the world's first true scientist because he was the first to systematically combine rigorous mathematical theory with repeatable, controlled experimentation. He didn't just observe the world, he designed experiments to test his hypotheses. He built apparatus, altered variables, meticulously recorded his results, and was unafraid to revise his theories when the evidence demanded it. This commitment to empirical proof over philosophical speculation marked a tectonic shift in how humans investigated the natural world. His work on optics didn't just explain how we see, it established a blueprint for how to know, a process of skeptical inquiry and verification that would become the bedrock of modern science centuries later. This passion for understanding the principles of motion and force extended beyond light into the realm of mechanics, where scholars sought to harness the power of physics for practical use. They were deeply engaged with the works of Greek engineers like Hero of Alexandria, but they moved far beyond mere imitation. A group known as the Banu Musa brothers Ahmad, Muhammad, and Al-Hasan were 3 prolific scholars in 9th century Baghdad who embodied this spirit of innovation. In their famous book, the Book of Ingenious Devices, they presented designs for 100 automata and mechanical contraptions that were centuries ahead of their time. These were not just toys, they were sophisticated demonstrations of principles involving pneumatics, hydraulics, and feedback control systems. The creations of the Banu Musa brothers showcased an astonishing level of ingenuity. They designed automatic fountains that could change their pattern at set intervals. They created a gas mask for workers descending into polluted wells. One of their most remarkable devices was a self-regulating lamp. It featured a float chamber and a valve system that would automatically maintain a constant level of fuel in the reservoir, ensuring the lamp burned with a steady flame without needing constant attention. This use of a feedback mechanism where the output of a system, the lowering fuel level, controls its input, the valve releasing more fuel, is a fundamental concept in modern engineering and robotics. Another of their devices was a mechanical wine dispenser that would mix wine and water in a specific ratio, a clever application of fluid dynamics that prevented a server from giving a guest an unexpectedly strong drink. These inventions reveal a society that valued not only theoretical knowledge, but also its application to improve daily life, comfort, and even safety. The most spectacular public demonstrations of this engineering prowess, however, were the magnificent water clocks and automata commissioned by the caliphs themselves. These were not merely timekeeping devices. They were theatrical marvels designed to showcase the wealth, power, and intellectual sophistication of the Abbasid court. The most famous was the Clock of the Elephants, a complex hydraulic clock that featured animated figures. As the hours passed, the mechanism would trigger a series of events. Doors would open to reveal figurines, balls would drop onto symbols, and robotic falcons would release balls into vases, all driven by the precise, relentless flow of water. Designing such a device required a deep understanding of siphons, gears, levers, and water pressure. The engineers had to calculate flow rates and gear ratios to ensure the movements were synchronized accurately with the passage of time. These clocks were a fusion of art and science, turning the abstract concept of time into a captivating public spectacle, and proving that the scholars of Baghdad had mastered the ability to make the inanimate world obey their commands through the clever application of physical laws. But of course, this incredible civilization, with its sprawling cities and vast populations, could not have been sustained by ideas alone. It required a more fundamental kind of nourishment, a mastery over the land itself that turned arid plains into breadbaskets. The intellectual energy of Baghdad was not confined to the House of Wisdom. It extended directly into the fields, orchards, and gardens that fed the empire. The scholars understood that a flourishing society needed a flourishing agriculture, and they approached farming with the same systematic, scientific rigor they applied to astronomy or medicine. This led to the creation of a new genre of scientific literature, the detailed agricultural manual, which transformed farming from a tradition passed down through generations into a documented, improvable science. These manuals were incredibly practical and comprehensive. Think of them as the complete farmer's almanac for the 9th century. They didn't just offer vague advice, they provided specific, tested instructions on every aspect of cultivation. A typical manual would begin with the crucial first step: how to assess a piece of land. It would explain how to test the soil, its texture, its color, its taste even, to determine whether it was best suited for wheat, barley, orchards, or vegetables. It would then give precise guidance on plowing techniques, the optimal depths for different seeds, and the exact amount of seed to sow per unit of land to avoid overcrowding. The timing of planting was meticulously detailed according to the solar calendar and the positions of the stars, connecting the work of the farmer directly to the cosmic charts being created by the astronomers. But the real science came in the management of the land itself. These texts championed sophisticated crop rotation systems, advising farmers not to exhaust the soil by planting the same crop year after year. Instead, they prescribed sequences, like following a grain crop with a legume such as lentils or chickpeas, which would help restore nitrogen to the earth, a principle that modern agronomy would confirm centuries later. They also covered grafting techniques to improve fruit trees, methods for protecting crops from pests, and the art of fertilizing using both animal manure and composted organic matter. Underpinning this agricultural revolution was a mastery of water, the most precious resource in a largely arid empire. The scholars and engineers of the era didn't just manage water, they worshipped it, developing hydraulic technology that was nothing short of miraculous. They perfected the ancient system of canats, underground channels that tapped into aquifer sources in the foothills and transported water for dozens of miles by gravity alone to arid plains and cities, minimizing evaporation in the searing heat. In the river valleys, they constructed complex networks of canals, dams, and water wheels. The Noria, a massive water wheel powered by the current of the river itself, could lift water high into irrigation channels to feed fields that lay far above the riverbank. The scientific management of this water was vital. Manuals provided detailed instructions on water rights and the fair distribution of irrigation water among farmers, often based on timed shares. This ensured that a complex, cooperative society could function without conflict over its most vital resource, turning regions like Lower Iraq into some of the most productive agricultural land on Earth. Alongside this practical science of farming grew a more scholarly pursuit, botany. Scholars were driven by a desire to systematically name, classify, and understand the plant kingdom, not just for food, but for medicine, industry, and sheer intellectual curiosity. The most influential figure in this field was Abu Hanifa al-Dinawari, a 9th-century scholar of Kurdish origin. His monumental work, the Book of Plants, was a landmark achievement. It was far more than a list. It was a comprehensive encyclopedia that described hundreds of plant species in meticulous detail. Al-Dinawari documented the entire life cycle of a plant, from its initial germination, through its growth and flowering, to the formation of its fruit and seeds. He described the anatomy of plants, their roots, stems, leaves, and flowers, with a scientific vocabulary that had not existed before in Arabic. He even explored the impact of the environment, noting how soil conditions and climate could affect a plant's growth and properties. This botanical knowledge had an immensely practical application in the field of pharmacology. Physicians like al-Razi and Ibn Sina needed to be certain that the medicines they prescribed were made from the correct plants. A mistake in identification could be fatal. Therefore, the botanists and the pharmacists worked hand in hand. Detailed botanical manuals included precise descriptions and often illustrations to help accurately identify medicinal herbs. They documented where each plant grew, when it should be harvested for maximum potency, and how it should be dried and stored. This created a reliable, standardized materia medica that a pharmacist in Cairo could use with the same confidence as a pharmacist in Baghdad, ensuring the safety and efficacy of treatments across the vast empire. The work of these botanists ensured that the advanced medical theories developed in the hospitals were grounded in a precise and reliable understanding of the natural world, completing a beautiful circle of knowledge where the earth's bounty was harnessed for the healing of its people. This deep connection to the land and its plant life naturally extended to the creatures that depended on it, both domestic and wild. The Abbasid Empire, with its vast cavalry, its caravans of camels crossing deserts, and its agricultural wealth, understood that its prosperity was inextricably linked to the health of its animals. This practical necessity sparked a sophisticated interest in veterinary medicine, a field that developed hand in hand with its human counterpart. Scholars produced detailed manuals for the care of horses, camels, birds of prey used in falconry, and livestock, blending empirical observation with the same systematic approach they applied to all other sciences. One of the most celebrated figures in this area was a man named Ibn al-Mundhir, whose work, the Book of Veterinary Medicine, became a standard reference. His text was remarkably comprehensive, covering everything from diagnosing illnesses through symptoms like a change in a horse's gait or the cloudiness in a falcon's eye, to surgical procedures for setting broken bones or treating wounds. He provided recipes for salves and medicines, instructions for dental care, and even advice on proper breeding to maintain the strength of valuable bloodlines. This wasn't just about economics. There was a clear sense of compassion and responsibility. These manuals often emphasize the ethical treatment of animals, instructing owners to provide adequate shelter, clean water, and rest, reflecting an understanding that an animal's well-being directly impacted its ability to work and serve. The stables and falconry mews became extensions of the clinic, where the principles of careful observation and evidence-based treatment were applied to ensure the health of creatures vital to the empire's military, trade, and leisure. Alongside this deeply practical knowledge, a more theoretical and encyclopedic fascination with the animal kingdom was flourishing, driven by the same intellectual currents that fueled all the other sciences. The translation of Greek texts, especially Aristotle's groundbreaking works like History of Animals and Parts of Animals, provided a powerful framework for this exploration. Aristotle's method of careful observation comparison, and classification inspired scholars in Baghdad to look at the natural world with fresh eyes. They weren't content to simply accept the Greek master's word. They sought to verify, correct, and expand upon it with their own investigations. This led to the creation of a distinct genre of Arabic literature known as the Kitab al-Hayawan, or Book of Animals. These weren't dry taxonomies. They were sprawling, fascinating compendiums that combined biology, medicine, folklore, and philosophy, aiming to capture the totality of animal life. The most monumental work in this tradition came from a scholar we have already met in other contexts, Al-Jahiz. His Book of Animals is a masterpiece of early zoology, a 7-volume work that is as much a work of literature as it is of science. Al-Jahiz roamed freely through his subject, describing the anatomy and behavior of everything from ants and bees to elephants and whales, but his genius lay in his powers of observation. He wrote in stunning detail about animal adaptation and ecology, noting how a predator's camouflage helped it hunt, or how the structure of a bird's beak was perfectly suited to its diet. He is perhaps most famous for proposing ideas that strikingly predate the theory of evolution by natural selection. He described a natural world in a constant state of struggle, where animals competed for resources, and where those with advantageous traits were more likely to survive, reproduce, and pass those traits on to their offspring. He even mused on how environmental factors could lead to the transformation of species over time. While his ideas were not part of a fully formed scientific theory like Darwin's, they reveal a mind grappling with the dynamic complexity of life in a way that was centuries ahead of its time. This intellectual project was carried forward by other great minds, most notably by al-Damiri in the 14th century, whose Lives of the Animals became an enduring encyclopedia. These works did more than just list facts. They engaged in serious scientific debate. Scholars critically examined Aristotle's claims, correcting him where their own observations differed. For instance, they challenged his description of the reproduction of bees or the anatomy of certain fish, demonstrating a commitment to empirical evidence over blind authority. The study of zoology also had practical spin-offs, particularly in the field of pharmacology. The properties of animal products, from the medicinal use of honey described in meticulous detail to the potential healing powers of various animal fats and organs, were catalogued with the same rigor as herbal remedies. This created a holistic understanding of nature's pharmacy, where the boundaries between the plant, mineral, and animal kingdoms were crossed in the pursuit of healing. The scholarly interest in animals, therefore, perfectly encapsulates the spirit of the age. It was a seamless blend of the intensely practical and the profoundly theoretical, all driven by an insatiable curiosity about the interconnected web of life. Yet this relentless drive to measure, map, and master the physical world found a surprising and beautiful counterpart in an art form that touches the very soul: music. For the scholars of Baghdad, the haunting melody of an oud or the complex rhythm of a drum was not merely entertainment. It was a window into the mathematical order of the cosmos itself. They inherited the ancient Greek idea that the universe was structured according to harmonic principles, that the motions of the planets created a music of the spheres, inaudible to human ears. This grand philosophical concept inspired them to study the music they could hear with the same scientific rigor they applied to astronomy or algebra. They saw music as a legitimate branch of mathematics, a science of sound where every note, interval, and rhythm could be precisely quantified, analyzed, and understood. This wasn't about stifling creativity. It was about uncovering the fundamental laws that made certain sequences of sound pleasing to the human ear, transforming the art of music into a sophisticated field of scholarly inquiry. At the heart of this musical science was the physics of sound. Scholars like the Banu Musa brothers, known for their mechanical devices, also turned their attention to acoustics. They investigated how sound was produced and traveled through the air, understanding it as a wave-like vibration. But their most significant breakthrough was in systematizing the relationships between pitches. They built upon the work of the ancient Greeks, particularly Pythagoras, who discovered that dividing a vibrating string into simple ratios produced consonant intervals. For example, shortening the string by half produced the octave, a ratio of 2 to 1. A ratio of 3 to 2 produced the perfect fifth, and 4 to 3 the perfect fourth. The scholars of Baghdad took this Pythagorean foundation and expanded it dramatically. They calculated incredibly precise musical scales, dividing the octave into more nuanced intervals than the Greek system allowed. They developed theories for the construction of frets on instruments like the oud to ensure perfect intonation, and they explored the acoustic properties of different materials, understanding how the shape and wood of an instrument's body would amplify and color its sound. This mathematical precision provided the foundation for a comprehensive theory of composition and performance. The most towering figure in this field was Abu Nasr al-Farabi, a true polymath of the 10th century whose work, the Grand Book of Music, is arguably the most important treatise on music from the entire medieval period. Al-Farabi didn't just describe how to play music, he created a complete scientific system for it. He meticulously classified musical instruments, describing their ranges and techniques. He developed a sophisticated system of notation to record melodies, an early attempt to preserve musical compositions beyond oral tradition, but his most profound contributions were in the realms of rhythm and mode. He analyzed rhythmic cycles with the complexity of a mathematician, identifying and naming dozens of distinct patterns, each with its own specific time signature and cultural association. He then mapped out the system of melodic modes, known as maqamat, which are the soul of Arabic music. Each maqam is not just a scale but a unique emotional landscape, with specific rules for progression and emphasis that evoke distinct feelings, from joy and longing to contemplation and ecstasy. Al-Farabi's genius, however, went beyond the technical. He was deeply fascinated by the psychological and physiological power of music, what we might now call music therapy. He argued that music was not a passive experience, but an active force that could directly alter the state of the listener's soul and body. Different maqamat, with their unique mathematical structures, could stir specific emotions and even produce physical effects. A lively rhythm in a joyful mode could lift depression and stimulate the heart, while a slow, contemplative melody in a somber mode could calm anxiety and soothe the nerves. He believed a skilled musician, acting as a kind of physician of the soul, could use this knowledge to guide a listener's emotional state toward balance and health. This idea of music as a therapeutic tool was revolutionary, positioning the musician as a scholar healer who understood the hidden connections between mathematical harmony, human emotion, and physical well-being. The influence of this sophisticated musical science permeated the very fabric of Abbasid society. The courts of the caliphs became renowned for their lavish musical gatherings, where the greatest performers of the age would showcase their artistry. But these were not mere parties. They were sophisticated salons where the theoretical knowledge of scholars like Al-Farabi met the virtuosity of master musicians. A performer would be expected to understand the theory behind the maqamat they were using, to be able to improvise within the strict rules of a rhythmic cycle, and to possess the skill to evoke the desired emotional response in their audience. This fusion of high theory and sublime practice elevated music to a respected intellectual and spiritual discipline. The musical theories developed in the scholarly circles of Baghdad did not remain locked in books. They traveled along trade routes, influencing musical traditions from Moorish Spain to the Persianate world, creating a shared language of melody and rhythm that echoed the cosmopolitan spirit of the empire itself, proving that the pursuit of knowledge could indeed produce something as intangible and as universally human as a beautiful song. Yet even as scholars were calculating the paths of planets and classifying species, the true soul of Abbasid Baghdad was being expressed in a more intimate and equally revered art form, the magic of the spoken and written word. In this culture, eloquence was not merely a talent, it was a supreme virtue, a sign of intellectual refinement and divine favor. The desert roots of the Arabs had long celebrated the power of poetry, seeing it as a source of tribal pride and a weapon sharper than any sword. but in the sophisticated, cosmopolitan atmosphere of Baghdad, this ancient tradition blossomed into something entirely new and breathtakingly complex. Poetry in Bell's letters, known collectively as adab, became the essential currency of social and intellectual life, flourishing side by side with scientific inquiry under the generous patronage of the same caliphs and courtiers who funded the House of Wisdom. This was a world where a brilliant verse could earn a poet a fortune in gold, and where a deep knowledge of literature was the passport to influence and respect. The concept of adab was far broader than our modern idea of literature. It encompassed everything from epic poetry and witty satires to elegant essays, historical anecdotes, and manuals on etiquette. To possess adab meant to be cultured, well-mannered, and knowledgeable across a wide range of subjects, a true Renaissance man centuries before the Renaissance. The ideal courtier or scholar was expected to be as comfortable debating a point of grammar as they were discussing a new astronomical theory, and to be able to cap a serious conversation with an apposite line of poetry. This created a vibrant literary ecosystem centered around the majlis, or salon. These were regular gatherings hosted by wealthy patrons, where poets, scholars, wits, and musicians would come together to perform, debate, and display their erudition. In these competitive forums, a poet's reputation was made or broken. The pressure to produce original, clever, and technically perfect verse on demand was immense, driving innovation and rewarding sheer brilliance. No figure better embodies the rebellious, innovative spirit of early Abbasid poetry than Abu Nuwas. A charismatic and controversial genius of the late 8th and early 9th centuries, Abu Nuwas deliberately turned the established conventions of Arabic poetry on their head. The classical qasida, or ode, typically began with a lament for a lost love at a deserted campsite, a prelude to praising the poet's tribe or a powerful patron. Abu Nuwas mocked this tradition. Instead of yearning for a Bedouin girl in the desert, he celebrated the vibrant life of the city, the taverns where wine flowed freely, the witty companions, and the beautiful cupbearers of both sexes. His poetry was urban, decadent, and deeply subversive, filled with a joyful irreverence that both shocked and delighted his audience. He wrote with breathtaking technical mastery, but used his skill to praise the pleasures of the moment rather than the glories of the past. His work offers a vivid, unforgettable portrait of the more libertine corners of Baghdad society, proving that literary scholarship could be as daring as any scientific experiment. While Abu Nuwas was breaking rules, other literary scholars were dedicated to defining and preserving them. As the language evolved and the empire incorporated non-Arab speakers, there was a growing concern for safeguarding the purity and power of classical Arabic. This gave rise to a sophisticated field of literary criticism. Critics like Al-Jahiz, whose work on animals we've already encountered, also wrote brilliant essays on rhetoric and style. In his Kitab al-Bayan wa al-Tabian, the Book of Eloquence and Demonstration, Al-Jahiz analyzed what made language effective and persuasive. He explored the psychological impact of different figures of speech, the importance of clarity, and the subtle art of irony. This wasn't dry analysis, it was a deep inquiry into the very nature of communication. Later, the critic Abdullah ibn al-Mu'taz would codify these ideas in his Kitab al-Badi, the Book of the Novel, which systematically identified and categorized the various poetic devices, metaphor, simile, antithesis, and paronomasia, that gave Arabic poetry its distinctive richness. These critics were the architects of eloquence, providing the theoretical framework that allowed poets to build their verbal palaces. This literary flourishing was made possible by a patronage system that viewed the support of artists as a fundamental duty of power and piety. The caliphs and their viziers competed with one another to attract the most talented poets and writers to their courts, offering lavish salaries, gifts, and prestigious positions. A powerful patron like the Barmakid viziers or Caliph Harun al-Rashid himself understood that surrounding oneself with brilliant minds was the ultimate status symbol. The relationship was symbiotic. A poet would compose panegyrics, praise poems extolling the patron's generosity, wisdom, and courage, thereby cementing their legacy. A particularly successful poem could spread the patron's fame across the empire, but patronage wasn't just about flattery. These patrons also valued wit, humor, and intellectual challenge. They supported the compilation of massive anthologies of poetry and prose, ensuring that the literary output of the age was preserved for future generations. This system ensured that a life dedicated to letters was not a life of poverty. It was a viable and respected career path, allowing artistic expression to thrive alongside and in constant dialogue with the scientific and philosophical revolutions of the age. Ibn al-Haytham's radical new theory of vision was only the beginning. His true legacy lies not just in the conclusion he reached, but in the meticulous, step-by-step process he used to get there. He didn't just think his way to a new idea, he built it, piece by piece, through a method of inquiry that was virtually unprecedented in its rigor. At the core of his approach was a profound skepticism toward accepted authority. He opens his book of Optics by stating that a seeker of truth must doubt all that has been handed down by tradition. This was a direct challenge to the towering figures of Aristotle and Ptolemy, whose emission theory had gone unquestioned for a millennium. For Ibn al-Haytham, truth was not found in the pages of an old book, no matter how revered its author, but in the undeniable evidence of controlled, repeatable experiments. His investigation into the camera obscura is a perfect example of this methodology in action. The basic principle, that light passing through a small hole into a dark room will project an inverted image of the outside scene, was known to others before him. But where previous thinkers had simply noted the phenomenon, Ibn al-Haytham turned it into a decisive laboratory tool. He didn't just observe the camera obscura, he experimented with it. He varied the size of the aperture, noting how a smaller hole created a sharper but dimmer image, while a larger hole made the image brighter but blurred. He understood that this proved light travels in straight lines from every point on an object, and that these rays cross at the pinhole, causing the inversion. This wasn't a passive observation, it was an active interrogation of nature, designed to test a specific hypothesis about the behavior of light. He used the camera obscura as a means to demonstrate that vision must work by these same physical principles, with light rays forming a similar, though much smaller, inverted image inside the eye itself. This commitment to experimental proof extended to his groundbreaking work on reflection and refraction. He constructed elaborate setups with polished metal mirrors of different shapes, flat, spherical, and parabolic. By carefully directing a narrow beam of light onto these surfaces and marking the angles of incidence and reflection, he was able to formulate the laws of reflection with a mathematical precision that had eluded his predecessors. He established that the angle at which light hits a surface is always equal to the angle at which it bounces away, and that both the incoming and outgoing rays lie in the same plane as a line perpendicular to the surface. His work on refraction, the bending of light as it passes from air into water or glass, was equally systematic. While he didn't deduce the exact sine law that Snell would later formulate, he correctly described the phenomenon and constructed tables of angles, creating a quantitative relationship between the angles of entry and the amount of bending for different materials. He even designed lenses based on this understanding, grinding pieces of glass into shapes that could magnify objects, laying the essential groundwork for the eventual invention of eyeglasses, telescopes, and microscopes centuries later. Perhaps his most profound contribution was the very structure of his inquiry, which established a blueprint for the modern scientific method. His process was a continuous cycle. He would begin with observation of a natural phenomenon, form a hypothesis to explain it, design a controlled experiment to test that hypothesis, meticulously record the results, and then use those results to either confirm, refine, or reject his initial idea. He was his own most stringent critic, always searching for potential flaws in his reasoning. This methodical approach, which combined abstract mathematical theory with tangible physical evidence, marked a tectonic shift in human thought. Before Ibn al-Haytham, natural philosophy was largely based on logical deduction from first principles. After him, the standard for truth became empirical verification. His book of optics is not a series of pronouncements. It is a detailed lab notebook, inviting the reader to follow his journey of discovery, to see the evidence for themselves, and to understand not just what he concluded, but how he knew it was true. In this way, Ibn al-Haytham did more than explain how we see. He taught humanity a new way to look at the world itself, with curiosity, skepticism, and an unwavering faith in the power of evidence. This new mathematical toolkit, forged in the crucible of the House of Wisdom, was never intended to be an abstract intellectual exercise. It was born from the urgent, everyday needs of a sprawling and sophisticated empire, and its power was immediately put to work solving some of the most complex social and structural problems of the age. Consider, for a moment, the intricate web of a Muslim family's life. When a merchant who had traded from the Indus Valley to the Mediterranean passed away, his estate might include multiple wives, children, brothers, sisters, and even distant cousins, all with specific, divinely ordained shares outlined in the Quran. The division of this estate was not a simple matter of splitting everything equally. The Quranic shares or fractions. A wife might be entitled to 1/8, a daughter to 1/2, a mother to 1/6, and these fractions had to be calculated against the entire estate after debts were paid. The potential for mathematical chaos was enormous. What happens if the sum of all the entitled shares adds up to more than one whole? This was a common puzzle known as the problem of the excluded heirs. It was precisely this kind of real-world challenge that scholars like Al-Khwarizmi were determined to solve. They applied their new algebra to create systematic methods for fair division. They developed algorithms to handle cases where the sum of the shares exceeded the estate, proportionally reducing each share until the total equaled 1. They created formulas to account for the presence or absence of certain relatives, turning what could have been a source of endless family conflict into a clear, just, and reproducible calculation. This was mathematics in the service of social harmony and divine justice. The same algebraic principles used to chart a star's path could now ensure that an orphan daughter received her rightful inheritance, demonstrating that the abstract beauty of numbers had a profoundly human purpose. The influence of this new mathematics reached even higher, literally shaping the skyline of Baghdad and other great Islamic cities. Architects and engineers, armed with the refined geometry from the translation of Euclid and the new trigonometric tables, embarked on building projects of breathtaking ambition. The most iconic of these was the dome. To construct a stable dome over a large square prayer hall, they had to solve the complex geometric problem of transitioning from a square base to a circular top. The solution was an ingenious architectural element called the squinch. A squinch is essentially a small arch or a series of concentric arches built across the corners of the square, gradually transforming the base into an octagon, then a 16-sided figure, and eventually into a circle ready to support the dome. Designing these squinches required a masterful understanding of spherical geometry and precise angular calculations. The result was not just structural stability, but an interior space that seemed to defy gravity, drawing the worshipper's eye upward toward the heavens in a perfect symphony of form and function. This geometric mastery extended to the very bricks and tiles of their buildings. The stunning geometric patterns that adorn mosques and palaces are not random decorations. They are visual demonstrations of advanced mathematical principles. Artists and architects used compass and straight edge to create infinite, repeating patterns based on complex symmetries and tessellations. They explored the possibilities of star polygons and Jiri tiles, developing a system that allowed for the creation of incredibly intricate, non-repeating patterns that still captivate mathematicians today. These patterns, often centered on a point of infinite regression, were more than art. They were a spiritual expression of the infinite nature of God, a visual representation of a universe bound by mathematical laws yet emanating from a single, unknowable source. The buildings themselves became textbooks of applied geometry, their walls whispering the secrets of angles, ratios, and cosmic order to all who entered. Beyond the peaceful pursuits of law and art, the scholars of Baghdad also turned their mathematical minds to the darker arts of secrecy and war. In a vast empire where messages had to travel thousands of miles through potentially hostile territory, secure communication was a matter of state security. This necessity gave birth to sophisticated cryptographic techniques, known as ilm al-taqi wa al-sitr, the science of signature and concealment. The most common method was a substitution cipher, where each letter of the alphabet is replaced by another. But the cryptographers of the era moved far beyond simple shifts. They developed complex polyalphabetic ciphers, where the substitution alphabet changes with each letter based on a pre-shared key, a method that would not be independently rediscovered in Europe for centuries. They also pioneered the use of frequency analysis to break codes, a technique famously detailed by the philosopher Al-Kindi. Al-Kindi realized that in any language, certain letters appear more frequently than others. By analyzing the frequency of symbols in a coded message, a cryptanalyst could begin to deduce which cipher symbol represented which common letter, cracking the code through statistical analysis rather than guesswork. This was a brilliant application of mathematical probability to the problems of the real world, turning the art of secret writing into a quantifiable science and setting the stage for a perpetual arms race between codemakers and codebreakers that continues to this day. The translation of ancient medical texts provided the essential theory, but it was within the purpose-built hospitals of Baghdad that this knowledge was tested, refined, and transformed into life-saving practice. These institutions, known as bimaristans, were far more than simple places of care. They were the world's first true centers for medical education, clinical research, and surgical innovation. The most advanced, like the Al-Adudi Hospital founded in the 10th century, were marvels of organization and hygiene that would not be seen in Europe for centuries. Their most striking feature was the system of separate wards for patients with different ailments. This was not merely for comfort, it was a profound understanding of contagion. Those suffering from fevers were isolated from those with wounds, and patients with infectious diseases like leprosy were housed in their own sections to prevent outbreaks. This logical segregation, a stark contrast to the chaotic, open halls of medieval European infirmaries, demonstrated a sophisticated grasp of public health that was literally built into the architecture. Within these specialized wards, surgery evolved from a desperate last resort into a respected medical discipline. Surgeons, armed with a growing understanding of anatomy from both Greek texts and their own observations, developed a remarkable array of specialized tools. Their kits contained finely crafted instruments made of steel and bronze, scalpels with razor-sharp, removable blades for making clean incisions, bone saws with finely set teeth for precise amputations, and a variety of forceps, hooks, and probes for manipulating tissue and extracting foreign objects. One of their most celebrated achievements was cataract surgery, a procedure to restore sight that required a steady hand and immense courage. The most common technique involved a hollow needle. The surgeon would carefully insert this needle through the white of the eye, near its edge, and gently maneuver it to the clouded lens, or cataract, which was then broken up and suctioned out. While the concept of a sterile field was still centuries away, these surgeons understood the importance of cleanliness, often using wine or vinegar as a primitive antiseptic to clean wounds and instruments, recognizing that it reduced the risk of the putrefaction that so often led to death. For more grave injuries or advanced diseases like gangrene, amputation was a terrifying but necessary procedure. The surgeons of the era had developed a systematic approach to minimize blood loss and maximize the patient's chance of survival. Before the operation, they would apply tight tourniquets above the incision site to restrict blood flow. Using a specially designed amputation knife, they would make a swift, circular cut through the skin and muscle down to the bone. A surgical saw, often a small, sturdy bow saw, was then used to cleanly sever the bone. The greatest immediate danger was hemorrhage. To control bleeding, surgeons employed a variety of techniques, from cauterizing the severed blood vessels with a red-hot iron to tying them off with ligatures made from silk or animal gut. While the lack of effective anesthesia meant the experience was agonizing, The speed and skill of these practitioners offered a fighting chance where none existed before, and their detailed manuals passed this hard-won knowledge on to future generations. The hospital itself was the engine that drove this medical progress. It functioned as a teaching institution where seasoned physicians guided students through medical rounds, discussing symptoms and diagnoses at the patient's bedside. This practical apprenticeship was complemented by formal lectures in the hospital's dedicated library, where students pored over texts by al-Razi and Ibn Sina. The hospital's pharmacy, or Saydalani, was a hub of innovation in its own right, where pharmacists compounded complex medicines from hundreds of meticulously cataloged ingredients, creating standardized formulas for everything from pain relief to digestive aids. This integrated system where observation, theory, surgery, and pharmacology all converged under one roof created a feedback loop of continuous improvement. A successful surgical technique observed in the ward would be documented in a new manual, and a new drug formulated in the pharmacy would be tested for its efficacy on the wards. The Baymaristan was more than a building. It was a living laboratory where the scholars of Baghdad demonstrated their deepest conviction. That knowledge, when applied with compassion and rigor, had the power to alleviate suffering and cheat death itself. Yet this ambition to map the heavens with greater accuracy than ever before inevitably led to a critical reappraisal of the very foundation of their science, the work of Claudius Ptolemy. His great treatise, known as the Almagest, had been the unquestioned authority on astronomy for centuries, a complex and brilliant system that explained the motions of the planets using a model of circles upon circles called epicycles and deferents. For the scholars of Baghdad, Ptolemy was not a figure to be worshipped, but a colleague to be questioned. They approached his work with deep respect for its mathematical sophistication, but also with a firm belief that observation must have the final say. This critical spirit ignited one of the most productive scientific dialogues in history, as they sought to test Ptolemy's theories against the cold, hard data of the night sky. The first step was perhaps the most straightforward, checking his numbers. As they made their own meticulous observations, they began to notice discrepancies. Ptolemy's predictions for the positions of planets, the timing of equinoxes, and the length of the solar year were slightly off. These were not minor errors, they were cracks in the foundation of the entire geocentric model, suggesting that the universe was not quite as Ptolemy had described it. This rigorous checking led to the creation of a new genre of scientific literature, the Zij. These were not just star charts, they were comprehensive astronomical handbooks that combined observational data, planetary tables, and computational methods. One of the earliest and most influential was the Zij al-Sindhind, compiled by a team of scholars including the great mathematician Al-Khwarizmi. This work attempted to correct Ptolemy's data by incorporating fresh observations and integrating mathematical knowledge from Indian sources. But the most systematic critic of Ptolemy was the brilliant scholar Abu Ishaq al-Battani, who worked at an observatory in northern Syria. Al-Battani's observations were renowned for their extraordinary precision. He recalculated the length of the solar year, arriving at a figure that is within minutes of the modern value. He produced vastly improved tables for the sun and the moon, and his detailed records of solar and lunar eclipses provided a data set that would be used by astronomers for centuries. His work, more than any other, demonstrated that Ptolemy's models, while mathematically elegant, were based on faulty parameters. The universe, it turned out, was even more precise and demanded even greater accuracy from those who sought to understand it. This drive for precision demanded more than just sharp eyes and patient record-keeping. It required a new generation of scientific instruments. The scholars of Baghdad became master engineers, designing and refining tools that could measure angles and track celestial movements with unprecedented accuracy. The most iconic of these was the astrolabe, a handheld computer made of brass that was the quintessential symbol of the medieval astronomer. But the astrolabes produced in the workshops of Baghdad were not simple copies of Greek models. They were marvels of complexity and artistry. An astrolabe is essentially a two-dimensional model of the three-dimensional sky. It consists of a central disk, called the mater or mother, which is engraved with a coordinate grid for a specific latitude. On top of this are interchangeable plates, each etched with the star patterns for a different latitude, and a pierced rotating disc called the rete that represents the ecliptic path of the sun and the positions of key stars. By suspending the instrument and aligning it with the North Star, an astronomer could solve dozens of problems, telling the time day or night, determining the direction to Mecca for prayer, calculating the height of a mountain, or predicting the rising and setting of any celestial body. The refinement of the astrolabe in Baghdad was a continuous process of innovation. Craftsmen and scholars worked together to add new features, such as trigonometric scales on the back that turned the instrument into a versatile calculator. They also developed larger, fixed versions for observatories that could be used for more precise measurements than a handheld device could allow. But for the most demanding work, even the astrolabe had its limits. This led to the creation of larger, more specialized instruments. The most important was the quadrant. While a simple quadrant is just a quarter circle marked with a 90-degree scale, the versions built in Islamic observatories were massive, precision-engineered structures. A large mural quadrant would be fixed permanently to a wall aligned perfectly north-south, allowing an astronomer to measure the altitude of a star as it crossed the meridian with incredible accuracy. Other observatories featured giant armillary spheres, rings within rings that represented the great circles of the celestial sphere, and sextants for measuring angles between stars. The ultimate expression of this commitment to instrumental precision was the establishment of permanent, state-funded observatories. These were not just buildings with a viewing platform. They were grand scientific institutions, equipped with a suite of massive, custom-built instruments that were feats of engineering in their own right. The most famous in Baghdad was the Shamsiyya Observatory, established under the patronage of Caliph Al-Mansur. Here, teams of astronomers could work together, night after night, taking coordinated measurements and comparing results. The existence of these observatories marked a fundamental shift in how science was done. It moved astronomy from the solitary pursuit of a scholar with an astrolabe to a collaborative, institutionalized enterprise based on the continuous collection of empirical data. This critical engagement with the past, combined with an unwavering commitment to technological innovation, allowed the astronomers of Baghdad to not just preserve ancient knowledge, but to correct it, refine it, and ultimately push the boundaries of human understanding of the cosmos further than anyone had before. But to think of these pursuits as separate streams would be to misunderstand the intellectual landscape entirely. For the vast majority of scholars in Baghdad, the study of the natural world and the contemplation of the divine were not opposing forces. They were two complementary paths leading toward the same ultimate truth. This wasn't a simplistic harmony, but a complex, often tense, and deeply fruitful relationship that shaped the very character of their inquiry. Many of the greatest scientific minds were also deeply engaged theologians, and they saw no contradiction in this. A man like al-Biruni, who calculated the Earth's circumference with stunning accuracy, also wrote extensively on comparative religion. The physician Ibn Sina, whose medical canon would dominate for centuries, was also a philosopher who sought to construct a unified system of all knowledge, from physics to metaphysics. For them, the universe was a single, grand creation, and to investigate its workings through observation and reason was, in itself, a form of devotion, a way to better understand the wisdom and power of the Creator. This worldview was profoundly shaped by a pivotal concept, the idea of the two books. The first was the revealed book, the Quran, the sacred text believed to be the literal word of God. The second was the book of nature, the entire physical universe, which was seen as another manifestation of God's creative act. Since both books originated from the same divine author, they could not fundamentally contradict one another. Any apparent conflict between a verse of scripture and an observation of nature was not a sign of error in faith or reason, but rather an indication of a flaw in human interpretation. This framework gave scholars a powerful mandate to investigate the natural world. If a careful astronomical observation seemed to conflict with a literal reading of a Quranic passage about the heavens, The task was not to reject the observation, but to delve deeper into the possible symbolic or allegorical meanings of the scripture. This approach encouraged a remarkable degree of intellectual freedom, allowing science to proceed without being constantly shackled by biblical literalism of the kind that would later cause such conflict in Europe. The engine driving this reconciliation was the discipline of Kalam, or Islamic theology. The practitioners of Kalam, the Mutakalimun, were masters of logical argumentation, and they eagerly adopted the tools of Greek philosophy, particularly Aristotelian logic, to defend and articulate Islamic doctrine. This engagement had a direct and positive impact on scientific thinking. Theologians debating the nature of God's attributes, for instance, developed sophisticated concepts of causality, infinity, and the atom that forced a more rigorous way of thinking about the physical world. When they argued about whether the world was created in time or was eternal, they were grappling with the same fundamental questions about cosmology that occupied the astronomers. This theological training instilled a habit of mind that valued logical consistency, systematic argument, and the critical examination of premises, skills that were directly transferable to scientific investigation. A scholar trained to deconstruct a complex theological argument with logical precision was well equipped to analyze a flawed astronomical model or identify an error in a medical text. However, this relationship was not without its famous and dramatic tensions. The most significant conflict arose from the attempt by philosophers like Al-Farabi and Ibn Sina to create a complete, rational system of reality based heavily on Neoplatonic ideas. Their systems, while brilliant, led to conclusions that clashed with core Islamic beliefs, such as the idea that the world was eternal rather than created, and that God's knowledge was only of universal truths, not of individual human events. This provoked a powerful backlash, most famously from the towering figure Abu Hamid al-Ghazali. In his seminal work, The Incoherence of the Philosophers, al-Ghazali launched a devastating attack, not on science or reason per se, but on the specific metaphysical claims of the philosophers. He argued that their arguments for the world's eternity were logically flawed, and that their denial of God's knowledge of particulars and of bodily resurrection was pure heresy. Al-Ghazali's critique was a watershed moment. It was not an attack on the study of medicine, astronomy, or mathematics. In fact, he praised these as beneficial sciences. His target was the overreach of philosophy into matters he believed could only be known through revelation. The result of this great debate was not the suppression of science, but a refinement of its boundaries. Al-Ghazali's work effectively cordoned off certain metaphysical questions as beyond the province of human reason, steering intellectual energy back toward the observable, measurable world where mathematics and experimentation could yield reliable results. In a way, this helped to ground scientific inquiry in empiricism. The legacy of this complex interplay was a rich and nuanced intellectual tradition. It produced a society where an astronomer could adjust his models based on new observations without fear of contradicting his faith, and where a physician could seek natural causes for disease while still believing in the ultimate power of God. This dynamic tension between reason and revelation, far from stifling progress, created a vibrant arena for debate that pushed scholars to be more rigorous, more critical, and more creative in their pursuit of knowledge, demonstrating that faith and science could coexist in a relationship that was both challenging and profoundly productive. Yet for all its resilience and brilliance, no golden age lasts forever. The intellectual powerhouse that was Baghdad did not simply fade away. Its decline was a complex story of political fragmentation, external shock, and a slow but steady migration of knowledge to new centers of learning. The first cracks in the foundation began to appear long before the cataclysm of the 13th century. The vast Abbasid Empire, which had provided the stability and resources for the House of Wisdom to flourish, started to fracture from within. From the 9th century onwards, the central authority of the caliphs in Baghdad began to weaken. Provincial governors and military commanders gained increasing autonomy, carving out their own independent dynasties in places like Egypt, Spain, and Central Asia. These new rulers often sought to legitimize their power by becoming patrons of science and culture in their own right, establishing rival libraries and observatories. This was a double-edged sword for Baghdad. While it meant the Islamic world's intellectual flame continued to burn brightly, it was now distributed across a wider geography, diluting the unique concentration of talent that had made the city the undisputed center of the scholarly universe. This political decentralization was exacerbated by economic strain. Maintaining the vast translation projects, funding observatories, and supporting thousands of scholars was an incredibly expensive endeavor, funded by the immense tax revenues of a unified empire. As the empire splintered, that revenue stream was interrupted. Patronage became more localized and less reliable. A scholar might find a generous patron in Cairo under the Fatimids or in Bukhara under the Samanids, but the kind of massive, centralized, state-sponsored research institution that was the House of Wisdom became increasingly difficult to sustain. The intellectual energy began to drift, following the money and the power to these new courts. Great thinkers like Ibn Sina and al-Biruni, for instance, spent their careers moving from one patron to another across Persia and Central Asia, their genius enriching the wider Islamic world, but no longer centered exclusively on Baghdad. Then came the event that serves as the symbolic end point of the era, the Mongol siege of Baghdad in 1258. The army of Hulagu Khan, the grandson of Genghis Khan, surrounded the city. The Abbasid Caliph, underestimating the threat, failed to mount an effective defense. The siege was brutal and short. When the walls were breached, the Mongols unleashed a wave of destruction that is seared into historical memory. The accounts, though likely exaggerated, speak of rivers of ink flowing from the destroyed libraries as countless books were thrown into the Tigris, and of pyramids of skulls from the massacred populace. The House of Wisdom, along with countless other libraries, was utterly destroyed. The Caliph himself was executed, while the Mongols would later adopt and even promote the scientific traditions of the lands they conquered. Under the Ilkhanate in Persia, for example, the sack of Baghdad was a traumatic, civilization-ending event for the city itself. It wasn't just the loss of books and buildings, it was the annihilation of an entire ecosystem, the networks of scholars, the chains of teacher-student relationships, and the institutional memory that had taken centuries to build. The city's role as the primary engine of global knowledge production was extinguished almost overnight, but to place the entire blame on the Mongols would be too simple. The intellectual decline was already underway, and the torch of learning had already been passed. In the West, Islamic Spain, or Al-Andalus, had been a major center of scholarship for centuries, with cities like Cordoba and Toledo rivaling Baghdad. After the fall of Toledo to Christian forces in 1085, a remarkable translation movement began, this time from Arabic into Latin. European scholars, often working with Jewish and Muslim colleagues, flocked to Toledo to translate the works of Al-Khwarizmi, al-Razi, Ibn Sina, and others. This massive transfer of knowledge, fueled by the scholarly treasures preserved in Andalusian libraries, became the direct catalyst for the European Renaissance. The works that had been synthesized and advanced in Baghdad were now being eagerly absorbed in Paris, Oxford, and Bologna, laying the groundwork for the scientific revolution. Simultaneously, other centers in the Islamic world were rising to prominence. Under the Mamluks in Cairo and Syria, scholarship continued, with impressive institutions like the Maristan of Kalawan combining hospital and teaching functions. In Persia, the Mongol Ilkhanids eventually patronized their own great observatory at Maraghe, where Nasir al-Din al-Tusi produced astronomical tables that would influence Copernicus. Later, the Timurid and Ottoman empires would foster their own scientific traditions. The decline of Baghdad, therefore, was not the death of Islamic science, but rather its diaspora. The seeds planted and cultivated along the Tigris had been scattered by the winds of political change and conquest, taking root in new soils from the Iberian Peninsula to the borders of India. The great project that began in the House of Wisdom, the preservation, critique, and expansion of human knowledge had become too big for any single city to contain, its legacy enduring not in one place, but in the very fabric of the modern world it helped to create. So as we reach the end of this journey, the true wonder of Baghdad's golden age is not found in any single discovery, but in the breathtaking scope of the entire endeavor. We have walked through halls where mathematicians gave us the algorithms that power our digital world and the algebra that unlocked the secrets of equations. We have looked over the shoulders of astronomers who mapped the heavens with painstaking precision, and physicians who turned hospitals into centers of healing and learning. We have listened to the philosophers debating the nature of reality and the theologians grappling with faith and reason. We have seen engineers build ingenious devices and alchemists lay the foundations for modern chemistry. From the intricate laws governing society to the mathematical principles behind a beautiful song, there was virtually no field of human inquiry that was not advanced, systematized, or reinvented within this vibrant intellectual culture. This was not merely an age of innovation, it was a monumental act of preservation. At a time when much of the ancient world's knowledge was scattered, fragmenting, or at risk of being lost forever, the scholars of the House of Wisdom undertook history's most ambitious rescue mission. They sought out manuscripts from the crumbling libraries of the Byzantine Empire, from the learned centers of India, and from the philosophical schools of Persia. They didn't just hoard these treasures, they translated them, critiqued them, and fused them into a new dynamic body of knowledge. The works of Plato and Aristotle, the geometry of Euclid, the medicine of Galen, these pillars of classical thought were saved from the dust of history by the painstaking efforts of translators who saw themselves as guardians of a shared human heritage. Without this great translation movement, the intellectual light of antiquity might have flickered out entirely, leaving a much darker path for the centuries that followed. And it is this very act of preservation that directly ignited the European Renaissance, when scholars in places like Toledo, Spain, began translating these Arabic texts into Latin in the 12th century. It was like a dam bursting. Europe, which had languished in what we often call the Dark Ages, was suddenly flooded with 1,000 years of accumulated knowledge, now refined and expanded by Islamic scholars. The works of Ibn Sina became the standard medical textbook in European universities for 500 years. The algebra of Al-Khwarizmi provided the mathematical language for a new scientific age. The astronomical models and critiques developed in Baghdad provided the very problems that thinkers like Copernicus and Kepler would later seek to solve. The European Renaissance was not a spontaneous rebirth. It was a direct inheritance, a passing of the torch from the scholars of Baghdad who had kept it burning brightly. Which brings us to a final, poignant reflection. The story of Baghdad's House of Wisdom is a powerful testament to what humanity can achieve when curiosity is valued above conflict, when diversity is seen as a strength, and when knowledge is pursued for the benefit of all. It shows us that progress is not inevitable, it is fragile. It requires stability, patronage, and a culture that celebrates inquiry. The bustling, multicultural streets of Baghdad, where Christians, Jews, Muslims, and Zoroastrians worked side by side, created a unique ecosystem where ideas could cross-pollinate and grow in ways that were impossible in more homogeneous or insular societies. The eventual decline of this center reminds us that such golden ages are precious and must be nurtured. The legacy of these scholars is not confined to history books. It is embedded in the very fabric of our modern world, from the numbers on our screens to the scientific method that guides our research. It's a legacy that challenges us to support our own centers of learning and to value the free exchange of ideas. And so we turn it over to you. After exploring this incredible period, which field of study captures your imagination the most? Is it the medical breakthroughs of al-Razi and Ibn Sina, the astronomical marvels of the great observatories, the philosophical debates that shaped centuries of thought, or perhaps the musical theories of al-Farabi? Let us know in the comments below which chapter of this story you find